We live in a world of 3 dimensions of space, yet some of the greatest minds believe there are more hidden, unseen dimensions that shape everything we know. Tonight, we embark on a journey beyond sight, beyond perception, into realms that exist all around us, yet remain invisible to our limited senses. Imagine for a moment that everything you see around you is merely a shadow of a greater reality. A reality that extends beyond the 3 dimensions our minds have evolved to perceive. When we look at the night sky, filled with countless stars and distant galaxies, we are seeing only what light can tell us, only what our eyes can detect. But what if the universe holds secrets in places we cannot see, in dimensions folded away from our perception? What if our 3-dimensional world is simply a slice of something far more complex? Throughout human history, we have expanded our understanding of the world. From flat Earth theories to the realization that we live on a sphere. From believing the sun orbited Earth to discovering our planet is but one of many circling an ordinary star in an ordinary galaxy among billions. Each revelation has humbled us. Each discovery has shown that reality is greater than our initial perception. And now, we stand at the threshold of perhaps the most profound expansion of our cosmic perspective since Copernicus. The mathematics that describes our universe with such precision hints at something remarkable. Hidden dimensions, curled up so tightly we cannot see them, yet potentially influencing everything from the behavior of fundamental particles to the very expansion of the universe itself. As we journey through this exploration together, we will leave behind the comfortable confines of our 3-dimensional thinking. We will venture into conceptual spaces where intuition fails and only the language of mathematics can guide us. Picture yourself as a 2-dimensional being living on the surface of a piece of paper. Your entire existence would be confined to forward, backward, left, and right. The concept of up and down would be not just invisible to you, but inconceivable. Now imagine a 3-dimensional object, like a sphere, passing through your flat paper world. What would you see? Not the sphere in its entirety, but a series of circles appearing from nowhere, expanding, contracting, and then disappearing. Magic, you might think, a miracle. But no, simply an encounter with a higher dimension. Are we perhaps like those flat beings? Are there phenomena in our universe that seem mysterious or inexplicable because they represent higher dimensional objects passing through our limited 3-dimensional perception? The mathematics of modern physics suggests this might indeed be the case. When Einstein unified space and time into space-time, he was already pointing us toward a 4-dimensional view of reality. But theoretical physicists now speak of 10, 11, or even 26 dimensions. These aren't dimensions of consciousness or spiritual planes, but actual physical dimensions of space, curled up so tightly at the quantum level that they remain hidden from our everyday experience. Is our universe truly limited to length, width, and height? Or are there more dimensions existing alongside us, perhaps separated by nothing more than the limitations of our perception? The answers might reshape our understanding of reality itself. They might explain mysteries that have puzzled scientists for generations, from the weakness of gravity to the nature of dark matter and dark energy. They might even provide the key to unifying all the forces of nature into a single, elegant theory. So let us begin this journey into the unseen, into the hidden architecture of reality. Let us explore the possibility that our universe is far stranger, far more magnificent than what meets the eye. In the words of physicist Richard Feynman, nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry. Perhaps these hidden dimensions are the threads that complete the cosmic fabric, waiting patiently for us to discover their intricate patterns. As we proceed, we will encounter mind-bending concepts and counterintuitive ideas. We will hear from theorists who propose that our entire universe might be a membrane floating in a higher dimensional space. or that tiny vibrating strings in dimensions too small to detect, might be the fundamental building blocks of all matter and energy. We will explore how these hidden dimensions might reveal themselves in our particle accelerators, or in subtle variations in the force of gravity. The journey ahead will challenge our imagination and expand our conception of what is possible. It will take us from the familiar world of our everyday experience to the very frontiers of theoretical physics. And perhaps, by its end, we will never look at reality quite the same way again. Before we can venture into the mysterious realm of hidden dimensions, we must first understand the dimensions we already know and experience every day. Our familiar world consists of 3 spatial dimensions plus time, which together form the foundation of our reality. Let us begin with the first dimension. Imagine a straight line, extending infinitely in both directions. If you were a being living on this line, you could only move forward or backward. You would have no concept of left or right, up or down. Your universe would be fully described by a single number, your position along that infinite line. This is the first dimension, length, and it is the simplest spatial dimension we can imagine. Now let us add a second dimension. Imagine our line extends sideways, creating a flat plane that stretches infinitely in all directions. If you were a being living on this plane, you could move forward and backward, left and right. Your position would be described by 2 numbers, your coordinates on this infinite sheet. This is the second dimension, width, and combined with length, it creates the concept of area. In our everyday experience, we encounter many 2-dimensional objects: a sheet of paper, the surface of a lake on a still day, a painting or a photograph. These are all approximately 2-dimensional, having negligible thickness compared to their length and width. Yet even these examples exist in our 3-dimensional world. A truly 2-dimensional universe would be impossible for us to fully visualize from within our 3-dimensional perspective. Let us now add the third dimension, height. With this addition, we create the spatial world we inhabit. We can move forward and backward, left and right, up and down. Our position is now described by 3 numbers, our coordinates in 3-dimensional space. This dimension gives us the concept of volume. Every object in our everyday experience has length, width, and height. This 3-dimensional framework allows for the complexity and richness of our physical world. Our brains have evolved to navigate and understand this 3-dimensional reality. We can perceive depth through various visual cues, the way objects overlap one another, the subtle differences in what each eye sees, the way things appear smaller as they recede into the distance. Our minds construct a 3-dimensional model of the world from these cues, allowing us to catch a ball, climb a tree, or navigate a crowded room. But our perception has limits. We cannot directly see inside a solid object. We cannot observe all sides of a cube simultaneously. Our perceptual apparatus gives us only a partial view of the 3-dimensional world, a series of 2-dimensional projections that our brains must interpret. The 3 dimensions of space have been recognized since ancient times. The Greek mathematician Euclid formalized many properties of 3-dimensional space in his Elements, written around 300 BCE. For most of human history, these 3 dimensions were considered absolute and complete. But in the late 19th and early 20th centuries, a revolutionary idea emerged that would forever change our understanding of the universe. Time, it seemed, could be considered as a 4th dimension. When we arrange to meet a friend, we specify not only the location in 3-dimensional space, but also a time. 4 numbers are required to fully describe the event: 3 for the spatial coordinates and 1 for the temporal coordinate. This 4-dimensional framework is what physicists call space-time, and it forms the foundation of Einstein's theories of relativity. Unlike the 3 dimensions of space, which we can move through freely in any direction, time appears to flow in only one direction. We move forward through time at a constant rate, unable to pause, reverse, or jump ahead. This fundamental difference led physicist Hermann Minkowski, who formalized the mathematics of spacetime, to treat time differently in his equations, giving it what mathematicians call an imaginary value. Einstein's theory of special relativity, published in 1905, revealed that space and time are intimately connected. As objects approach the speed of light, strange effects begin to occur. Time slows down, lengths contract, and simultaneity becomes relative. Events that appear to happen at the same time to one observer may occur at different times for another observer, moving at a different velocity. These effects have been confirmed countless times in laboratory experiments. Atomic clocks placed on high-speed aircraft return slightly behind identical clocks that remained on the ground. Particles in accelerators live longer than they should because, from our perspective, time passes more slowly for them as they approach the speed of light. The GPS system in your phone or car would quickly become inaccurate if it did not account for these relativistic effects. The theory of general relativity, which Einstein published a decade later in 1915, went even further. It proposed that gravity is not a force in the conventional sense, but a curvature of space-time caused by mass and energy. The presence of a massive object like the Sun creates a depression in the fabric of space-time, similar to how a bowling ball placed on a mattress would create a depression in the mattress. Other objects, like planets, follow the curves in this space-time fabric, resulting in what we perceive as orbital motion. General relativity has passed every experimental test devised to date. It predicted the bending of starlight around the Sun, the precise orbit of Mercury, the existence of black holes, and the gravitational waves that were finally detected directly in 2015 by the LIGO observatories. The 4 dimensions of spacetime, 3 of space and 1 of time, form our current understanding of the macroscopic universe, but they may not be the end of the story. When physicists attempt to reconcile general relativity with quantum mechanics, the theory that describes the behavior of particles at the smallest scales, they encounter persistent mathematical inconsistencies. These inconsistencies hint at the possibility that our 4-dimensional model is incomplete. It's worth noting that even in our familiar dimensions, there are aspects that challenge our intuition. Consider the concept of fractional dimensions, which arise in certain mathematical and physical contexts. A coastline, viewed at different scales, exhibits properties that can be described by a dimension between 1 and 2. Some natural structures, like fern leaves or snowflakes, display what mathematicians call fractal dimensions, where patterns repeat at different scales in a way that creates complexity from simple rules. Our direct sensory experience of the world is surprisingly limited. The light we see represents only a tiny fraction of the electromagnetic spectrum. Beyond the visible spectrum lie radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, all invisible to our unaided eyes. Similarly, our ears detect only a limited range of sound frequencies, and our other senses have their own limitations. Technology has expanded our perceptual reach dramatically. Radio telescopes reveal cosmic structures invisible to optical telescopes. Electron microscopes show us the world of the very small. Medical imaging technologies like MRI and CT scans allow us to see inside the human body without invasive procedures. Each of these technologies extends our perception into realms that were once hidden from us, just as theories of extra dimensions propose to extend our conceptual understanding beyond the familiar 3 dimensions of space. The limits of our perception raise a profound question. If we can miss so much with our ordinary senses, even within the 3 spatial dimensions we know exist, what else might we be missing? Could there be entire dimensions, curled up so tightly or oriented in such a way that they escape our notice completely? Consider how a 3-dimensional object casts a 2-dimensional shadow. Similarly, our 3-dimensional world might be a kind of projection or shadow of a higher dimensional reality. The mathematics that describes our universe with such precision seems to point in this direction. Equations that include extra dimensions often resolve paradoxes and inconsistencies that plague theories limited to 4 dimensions. Our journey into the hidden dimensions begins with this understanding of our limitations. The world as we perceive it may be just a slice of a much greater reality. The 3 dimensions of space and 1 dimension of time that form our everyday experience may be merely the dimensions that our brains evolved to perceive, the dimensions relevant to our survival as a species on a moderate-sized planet orbiting an average star. As we venture further into the exploration of hidden dimensions, we will build upon this foundation. The familiar dimensions provide our starting point, but mathematics and theoretical physics will be our guides as we explore the possibility of dimensions beyond our direct experience. We will see how these extra dimensions might be necessary to explain the fundamental forces of nature, the behavior of particles at the quantum level, and perhaps even the very origin and fate of our universe. The idea that reality extends beyond our immediate perception is not new. Throughout history, humans have sensed that there is more to the universe than meets the eye. From Plato's allegory of the cave, where prisoners mistake shadows for reality, to Edwin Abbott's 19th century novel Flatland, which explored how a 2-dimensional being might perceive interactions with a 3-dimensional world, we have long contemplated the limits of our perception and the possibility of realities beyond our immediate grasp. Modern physics has given mathematical substance to these philosophical speculations. The extra dimensions proposed by contemporary theories are not metaphors or analogies, but actual physical dimensions, potentially as real as length, width, and height. Their effects may be subtle in our everyday experience, but they could be fundamental to the deepest workings of the universe. As we conclude this exploration of the dimensions we know, let us remember that our understanding is always evolving. The 3-dimensional view that seems so natural to us now was once a revolutionary concept. The idea of time as a 4th dimension, intimately woven with space, would have seemed bizarre to scientists just 2 centuries ago. Perhaps centuries from now, the concept of 10 or 11 dimensions will seem as intuitive and obvious as our current 4-dimensional model does today. Our journey continues as we explore how the idea of hidden dimensions first emerged in the history of physics, and how these early theories laid the groundwork for the more sophisticated models of string theory and beyond. But we carry with us this essential insight. The dimensions we know may be just the beginning of a much richer, more complex reality awaiting our discovery. The human imagination has long contemplated realities beyond our immediate perception. From ancient mystical traditions to early scientific speculations, the idea that our visible world might be just a portion of a larger reality has persisted throughout history. But it was not until the early 20th century that higher dimensional theories began to take a rigorous mathematical form within the realm of physics. The story begins in 1914, when a young German mathematician named Theodor Kaluza was contemplating one of the most significant problems in physics. At that time, physicists recognized 2 fundamental forces in nature: gravity, which Einstein had recently reformulated in his general theory of relativity, and electromagnetism, which had been unified by James Clerk Maxwell in the 19th century. These 2 forces appeared completely different in their mathematical descriptions and physical behavior. Kaluza had a remarkable insight. He wondered what would happen if Einstein's equations of general relativity, which describe gravity in 4 dimensions, were extended to 5 dimensions, with 1 extra spatial dimension added to the familiar 3 dimensions of space and 1 of time. When he performed this mathematical exercise, something extraordinary emerged from his equations. The expanded equations naturally split into 2 sets. One set was identical to Einstein's original equations describing gravity in 4 dimensions. But remarkably, the second set was identical to Maxwell's equations of electromagnetism. Simply by adding an extra dimension to Einstein's theory, Kaluza had found a way to describe both gravity and electromagnetism within a single mathematical framework. It seemed that these 2 fundamental forces previously thought to be entirely separate, might be unified as different aspects of a single force existing in 5 dimensions. Kaluza sent his paper to Einstein in 1919, who was initially skeptical but eventually became convinced of its merit. Einstein helped Kaluza publish his work in 1921. However, the theory faced an obvious problem. If there is a 5th dimension, why don't we see it? Why is our experience limited to 3 spatial dimensions and time? The answer came a few years later from the Swedish physicist Oskar Klein, who independently developed similar ideas. Klein proposed that the 5th dimension is curled up, or compactified, into an incredibly small circle at each point in our 4-dimensional spacetime. This circle would be so tiny, perhaps at the Planck scale of approximately 10 to the negative 35 meters, that it would be far too small for us to detect with any conceivable experiment. To understand this concept, imagine an ant walking along a thin garden hose. From far away, the hose appears to be just a 1-dimensional line. Only upon close inspection can we see that at each point along this line, there is actually a tiny circle going around the hose. The ant can move along the length of the hose, but it can also move around the circumference at any point. Similarly, Klein suggested that particles in our universe can move through the 3 large spatial dimensions that we perceive, but they can also move through this tiny, curled-up 5th dimension that escapes our notice because of its incredibly small size. This unified theory, now known as Kaluza-Klein theory, was a revolutionary idea that for the first time suggested extra dimensions might be more than just mathematical curiosities. They might be essential to understanding the fundamental physics of our universe. The theory provided a geometrical interpretation of electromagnetism, suggesting that what we perceive as electromagnetic forces might actually be manifestations of the geometry of a higher dimensional space, just as Einstein had shown that gravity could be understood as the curvature of 4-dimensional spacetime. Despite its elegance, the original Kaluza-Klein theory had several problems that prevented it from becoming a complete unified theory of physics. It didn't account for the newly discovered nuclear forces, and it predicted a particle that has never been observed. Furthermore, when quantum mechanics entered the picture, new complications arose that the theory couldn't address. Nevertheless, the core insight of Kaluza-Klein theory, that extra dimensions might unify different forces of nature, would prove remarkably prescient. It established a template that later theories would follow and expand upon. The idea that fundamental aspects of reality might be explained by the geometry of hidden dimensions had entered the scientific imagination and would never leave it. After the initial excitement, interest in higher dimensional theories waned for several decades as physicists focused on developing quantum field theory, which was spectacularly successful in describing the behavior of particles and forces at the subatomic level. The standard model of particle physics emerged from these efforts, unifying the electromagnetic force with the weak nuclear force and providing a framework for understanding the strong nuclear force as well. Yet even as the standard model accumulated impressive experimental confirmations, theoretical problems persisted. The standard model didn't include gravity, and attempts to incorporate it led to mathematical inconsistencies. Moreover, the theory required numerous arbitrary parameters that had to be measured experimentally rather than derived from first principles. Many physicists felt that a more fundamental theory must exist. A revival of interest in higher dimensional theories began in the 1970s and 80s, spurred by developments in particle physics and early versions of string theory. Physicists began to reconsider the Kaluza-Klein approach, but now with more dimensions and in the context of quantum field theory. One significant development was the theory of supergravity, which combined the idea of supersymmetry, a proposed symmetry between fermions and bosons, with general relativity. In 11 dimensions, supergravity achieved its most elegant formulation. This 11-dimensional theory could potentially describe all the known particles and forces, including gravity, within a single mathematical framework. Around the same time, string theory was emerging as a promising approach to quantum gravity. Initially developed as a theory of the strong nuclear force, string theory was repurposed when it was discovered that it naturally included a particle with the properties of the graviton, the hypothetical particle that carries the gravitational force. Crucially, string theory only made mathematical sense if it operated in more than 4 dimensions, specifically in 10 dimensions for most versions of the theory. The parallel development of supergravity and string theory, both requiring extra dimensions, suggested that higher dimensional spaces might indeed be fundamental to our understanding of physics. These extra dimensions were not arbitrary additions, but seemed to be required for the mathematical consistency of theories that attempted to unify quantum mechanics and general relativity. In the late 1970s, a group of physicists, including Peter Freund and Mark Rubin, discovered that 11-dimensional supergravity could be compactified to yield a 4-dimensional theory that resembled the standard model of particle physics. This marked a significant advance over the original Kaluza-Klein theory, showing that the properties of the extra dimensions could potentially explain the complex pattern of particles and forces observed in our 4-dimensional world. The 1980s saw further development of these ideas. The 6 or 7 extra dimensions required by string theory or supergravity were typically compactified on special geometrical shapes. The precise properties of these shapes, such as their topology and symmetries, would determine the physics we observe in our 4-dimensional world. This led to intense study of mathematical structures called Calabi-Yau manifolds, 6-dimensional spaces with properties that could produce something resembling the standard model when used as the extra dimensions in string theory. A major breakthrough came in 1984 with the discovery of anomaly cancellation in string theory by Michael Green and John Schwartz. This showed that certain versions of string theory were free from the mathematical inconsistencies that had plagued previous attempts to create a quantum theory of gravity. This discovery, often called the first superstring revolution, ignited enormous interest in string theory and its higher dimensional implications. As these theories developed, physicists began to explore the potential experimental signatures of extra dimensions. If these dimensions exist, could we detect them? The traditional view, dating back to Klein, was that extra dimensions would be compactified at the Planck scale, roughly 10 to the negative 35 meters, far too small to detect with any foreseeable technology. However, in the late 1990s, a new possibility emerged. Physicists, including Nima Arkani-Hamed, Savas Dimopoulos, and Gia Dvali, proposed what came to be known as the ADD model, suggesting that some extra dimensions might be much larger than the Planck scale, perhaps as large as a millimeter. These large extra dimensions could potentially be detected in high-energy particle collisions, or in precise measurements of gravitational forces at small distances. Around the same time, Lisa Randall and Raman Sundram proposed another model in which an extra dimension could be warped in such a way that gravity would be concentrated on a 4-dimensional brane within a 5-dimensional bulk. This warping could explain why gravity appears so much weaker than the other fundamental forces, a long-standing puzzle known as the hierarchy problem. These developments in the late 20th century transformed higher dimensional theories from mathematical curiosities to potentially testable scientific hypotheses. The Large Hadron Collider and other experiments began searching for signatures of extra dimensions, such as missing energy in particle collisions that might indicate particles escaping into hidden dimensions, or microscopic black holes that could form if gravity becomes stronger at small distances due to the effects of extra dimensions. While definitive experimental evidence for extra dimensions remains elusive, the theoretical case for their existence has only strengthened. The most promising candidates for a unified theory of physics, including string theory and its extensions, consistently require extra dimensions for their mathematical consistency. The evolution of higher dimensional theories illustrates a recurring pattern in the history of physics. Ideas that initially seem speculative or even mystical can, when formulated mathematically and connected to observable phenomena, become serious scientific hypotheses. From Kaluza's initial insight that a fifth dimension might unify gravity and electromagnetism to the elaborate geometries of modern string theory. The concept of hidden dimensions has evolved from a mathematical abstraction to a central feature of our most advanced physical theories. As we enter the 21st century, higher dimensional theories continue to develop in sophistication and scope. The discovery of M-theory in the mid-1990s, which unified the various string theories and 11-dimensional supergravity, suggested that even string theory might be just a special case of a more fundamental theory existing in 11 dimensions. Similarly, the discovery of the ADS-CFT correspondence, a relationship between gravitational theories in higher dimensions and quantum field theories in lower dimensions, has provided new mathematical tools for understanding quantum gravity and has found applications in fields as diverse as nuclear physics and condensed matter physics. The search for experimental evidence continues as well. While the Large Hadron Collider has not yet found direct evidence of extra dimensions, it has placed constraints on their possible sizes and properties. Gravitational wave astronomy, a field born with the LIGO detections in 2015, may eventually provide new ways to test higher dimensional theories. And theoretical physicists continue to refine their models, seeking predictions that can be tested with current or near-future technology. As we look back at the century-long development of higher dimensional theories in physics, we can see both continuity and change. The core insight of Kaluza and Klein, that unification might require extra dimensions, remains at the heart of modern approaches. But the mathematical sophistication of these theories has grown enormously, incorporating quantum mechanics, field theory, and advanced geometrical concepts that were unavailable to the early pioneers. The birth and development of higher dimensional theories illustrates a profound truth about physics. Our theories are not mere descriptions of what we can directly observe, but attempts to construct mathematical models that explain the patterns in our observations and predict new phenomena. Sometimes these models lead us to postulate entities or structures, like extra dimensions, that lie beyond our immediate perception, but might nevertheless be essential components of physical reality. In the next chapter, we will delve deeper into string theory, the most developed framework for understanding these hidden dimensions. We will explore how tiny vibrating strings moving through a 10 or 11-dimensional space-time might generate all the particles and forces we observe, and how the geometry of the extra dimensions might determine the properties of our universe. But as we do so, we will carry forward the fundamental insight of Kaluza and Klein that the dimensionality of our universe might be greater than what meets the eye, and that hidden within these extra dimensions might lie the keys to unifying our understanding of the physical world. Deep within the fabric of our universe, at scales far smaller than atoms, electrons, or even quarks, there may exist the most fundamental constituents of reality. Not particles, as we have long assumed, but tiny vibrating loops of energy, one-dimensional objects called strings. This is the central proposal of string theory, perhaps the most ambitious attempt in the history of physics, to provide a complete understanding of the fundamental nature of reality. And remarkably, this theory requires the existence of extra dimensions beyond the familiar 3 dimensions of space and 1 of time. Let us begin our exploration of string theory by understanding why physicists were driven to consider such a radical departure from previous theories. Throughout the 20th century, physicists developed 2 enormously successful frameworks for understanding the physical world. General relativity, Einstein's theory of gravity, describes the behavior of space, time, and matter at the largest scales, from the orbits of planets to the expansion of the entire universe. Quantum mechanics, and its extension quantum field theory, describes the behavior of particles and forces at the smallest scales, from atoms to subatomic particles. Both theories have been confirmed by countless experiments and observations. General relativity predicted gravitational waves, black holes, and the expansion of the universe, all of which have been observed. Quantum field theory predicted antimatter, the Higgs boson, and the precise behaviors of particles in accelerators, also all confirmed experimentally. Yet these two pillars of modern physics are fundamentally incompatible. When physicists attempt to apply the methods of quantum field theory to gravity, they encounter severe mathematical difficulties. Calculations produce infinite results that cannot be eliminated using the standard techniques of renormalization that work for the other forces. This suggests that at the Planck scale, approximately 10 to the negative 35 meters, where quantum gravity effects would become significant, our current theories break down completely. String theory emerged as an attempt to resolve this conflict. The basic idea is elegantly simple, though its implications are profound. Instead of treating fundamental particles as zero-dimensional points with no internal structure, string theory proposes that they are actually tiny, one-dimensional loops or segments of vibrating energy. Just as a violin string can vibrate in different patterns to produce different notes, these fundamental strings vibrate in different patterns to produce different particles. An electron, a photon, and a graviton would all be the same type of string, just vibrating in different ways. This simple change, from zero-dimensional points to one-dimensional strings, has remarkable consequences. Most significantly, string theory naturally includes a particle with the properties of the graviton, the hypothetical carrier of the gravitational force. Moreover, the mathematical infinities that plague attempts to quantize gravity disappear in string theory because strings are extended objects. The extended nature of strings means that interactions are spread out rather than occurring at a single point, smoothing away the troublesome infinities. But this elegant solution comes with a startling requirement. For string theory to be mathematically consistent, for its equations to make sense, the universe must have more than the 4 dimensions we commonly observe. Depending on the specific version of string theory, the total number of dimensions must be either 10 or 26. Why would the mathematics of tiny vibrating strings demand extra dimensions? The answer lies in the constraints on how strings can vibrate. In a one-dimensional string, there are certain types of vibrations that can lead to inconsistencies in the theory, specifically what physicists call anomalies. These anomalies would violate fundamental conservation laws and render the theory unphysical. However, if the strings exist in a spacetime with exactly the right number of dimensions, these troublesome vibrations can be shown to cancel out precisely, leaving a mathematically consistent theory. The original version of string theory, which included only bosons, the particles that transmit forces, required 26 dimensions. Later, when fermions, the particles that make up matter, were incorporated into the theory to create superstring theory, the requirement changed to 10 dimensions, specifically 9 spatial dimensions plus time. This raises an obvious question. If string theory demands 10 dimensions, but we only observe 4, where are the missing 6 dimensions? The answer, building on the insights of Kaluza and Klein discussed in the previous chapter, is that these extra dimensions are compactified, curled up so tightly that they escape our notice in everyday experience. To visualize this, imagine a garden hose viewed from a great distance. From far away, the hose appears to be a one-dimensional line. Only upon close inspection can we see that at each point along this line, there is actually a tiny circle, a second dimension wrapped around the hose. Similarly, at each point in our familiar 4-dimensional spacetime, string theory proposes that there are 6 additional dimensions, curled up into incredibly tiny complex shapes. The most widely studied shapes for these extra dimensions are called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xing-Tung Yau. These are 6-dimensional geometrical structures with specific mathematical properties that make them suitable as the extra dimensions in string theory. Calabi-Yau manifolds are extraordinarily complex, with numerous holes and handles that can be arranged in thousands of different configurations. The precise shape and size of these extra dimensions is not arbitrary. In string theory, the geometry of the extra dimensions determines the properties of the particles and forces we observe in our four-dimensional world. Different arrangements of the Calabi-Yau manifold would result in different patterns of particle masses, charges, and interactions. This leads to a profound insight. The fundamental constants of nature, quantities like the mass of the electron or the strength of the electromagnetic force, which in the standard model must be measured experimentally and inserted into the theory by hand, could potentially be derived from the geometry of the extra dimensions in string theory. What appears to us as arbitrary parameters might actually reflect the specific way in which the extra dimensions are compactified. However, this insight also leads to a challenge. Mathematical analysis reveals that there are an enormous number of possible Calabi-Yau manifolds, perhaps as many as 10 to the 500 different configurations. Each would correspond to a different possible universe with different physical laws. This vast collection of possibilities is sometimes called the string theory landscape, and it raises difficult questions about why our universe has the specific properties it does, rather than any of the countless alternatives. Some physicists see this as a serious problem for string theory, arguing that a fundamental theory should uniquely predict the properties of our universe. Others connect it to ideas from cosmology about the existence of a multiverse, suggesting that perhaps many or all of these possible configurations are realized in different regions of a much larger cosmos, and we find ourselves in a region with physical laws conducive to the existence of life. Despite these interpretive challenges, string theory remains the most developed framework for understanding physics at the Planck scale, where quantum gravity becomes significant. Its mathematical consistency and its ability to potentially unify all four fundamental forces within a single theoretical framework give it unparalleled power as a candidate theory of everything. In the mid-1990s, a series of insights led to what has been called the second superstring revolution. Physicists discovered a network of mathematical relationships called dualities that connected the 5 different versions of string theory that had been developed. These dualities suggested that the 5 theories were not truly distinct, but rather different perspectives on a single, more fundamental theory, which was named M-theory. M-theory requires 11 dimensions, one more than the 10 of superstring theory. This 11th dimension is not compactified in the same way as the other 6 extra dimensions. In M-theory, one-dimensional strings are no longer the only fundamental objects. The theory also includes 2-dimensional membranes, 3-dimensional volumes, and higher dimensional objects collectively called branes. The discovery of M-theory expanded the conceptual framework for understanding extra dimensions. In some formulations, our entire 4-dimensional universe could be understood as a 3-dimensional brane floating within a higher dimensional bulk. Other branes might exist within this bulk, potentially even parallel to our own, separated from us by distances measured in the extra dimensions. This brane world scenario has profound implications. If our universe is a brane within a higher dimensional space, then some aspects of reality might extend beyond our brane into the bulk. Gravity, in particular, might propagate through the bulk, explaining why it appears so much weaker than the other fundamental forces, which might be confined to our brane. These concepts may seem abstract, even bizarre, but they emerge naturally from the mathematics of string theory and M-theory. And crucially, they make predictions that could potentially be tested experimentally. For example, if gravity propagates through extra dimensions, its strength might deviate from the inverse square law at very small distances. Or if our universe is a brane within a higher dimensional bulk, we might observe energy disappearing from particle collisions as it escapes into the extra dimensions. The mathematical formalism of string theory is extraordinarily rich and complex. The theory involves concepts from quantum field theory, general relativity, and branches of advanced mathematics, including topology, differential geometry, and abstract algebra. Few areas of human knowledge require such a diverse set of sophisticated tools. Yet at its core, string theory rests on a remarkably simple idea that the fundamental constituents of reality are not point particles, but tiny vibrating strings. From this simple premise, combined with the principles of quantum mechanics and relativity, flows the requirement for extra dimensions and all the other exotic features of the theory. One of the most remarkable aspects of string theory is how it unifies the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. In conventional quantum field theory, each force is described by the exchange of a specific type of particle: a photon for electromagnetism, gluons for the strong force, W and Z bosons for the weak force, and the hypothetical graviton for gravity. In string theory, all of these force-carrying particles correspond to different vibrational modes of the same fundamental string. Moreover, the matter particles, electrons, quarks, and so on, also emerge as vibrational patterns of these same strings. Everything in the universe, from the electrons in your body to the photons of light entering your eyes as you read these words, from the nuclear forces binding atomic nuclei to the gravitational force holding you in your seat, all would be manifestations of these vibrating strings moving through a 10 or 11-dimensional space-time. This unification extends even further. In string theory, the laws of physics themselves, the equations that govern how particles move and interact, emerge from the geometry of the extra dimensions and the dynamics of strings. The separation between the laws of physics and the contents of the universe, which has been a basic assumption of science since the time of Newton, becomes blurred in string theory. The laws and the contents coexist as aspects of a deeper mathematical structure. Despite its mathematical beauty and conceptual power, string theory faces significant challenges. The most obvious is the lack of direct experimental evidence. The characteristic length scale of strings is thought to be roughly the Planck length, about 10 to the negative 35 meters, far smaller than anything we can directly probe with current or foreseeable technology. The energies required to directly observe stringy behavior would be about 10 to the 16th times higher than what the Large Hadron Collider can achieve. However, string theory might still make testable predictions for phenomena at accessible energies or distances. For example, certain configurations of the extra dimensions might predict specific patterns of particle masses or force strengths that could be compared with experiments. Or string theory-inspired models with large extra dimensions might predict deviations from general relativity at scales that could be tested in laboratory experiments. Another challenge comes from the vast landscape of possible string theory solutions, making it difficult to extract unique predictions from the theory. Some critics argue that if a theory can accommodate almost any set of physical parameters, it loses predictive power and therefore scientific value. Proponents respond that the theory still places significant constraints on what is physically possible, and that the apparent freedom might reflect a deeper principle we have yet to discover or connect to cosmological ideas about the multiverse. Despite these challenges, string theory has transformed our understanding of fundamental physics and the nature of spacetime. It has led to profound mathematical insights, including surprising connections between quantum field theories and gravitational theories through the ADS-CFT correspondence, a relationship between a gravitational theory in a higher dimensional space and a quantum field theory on its boundary. The extra dimensions required by string theory are not arbitrary additions, but essential components of the mathematical framework. They emerge naturally from the requirement that the theory be consistent both with quantum mechanics and with general relativity. In this sense, string theory does not merely suggest that extra dimensions might exist, it practically demands their existence. As we contemplate the implications of string theory and its extra dimensions, we are reminded of the power of mathematical reasoning to guide our understanding of physical reality. Throughout the history of physics, mathematical consistency and elegance have often pointed the way to new insights about the natural world, sometimes decades before experimental confirmation was possible. The prediction of antimatter by Dirac's equation, the prediction of the omega- particle from group theoretical considerations, and the prediction of the Higgs boson from symmetry principles are just a few examples of this pattern. Perhaps the extra dimensions required by string theory will follow this historical pattern, moving from mathematical necessity to experimentally confirmed reality. Or perhaps string theory will ultimately be superseded by some even more fundamental framework. In either case, the exploration of these ideas has already enriched our understanding of the possible nature of physical reality. As we conclude this exploration of string theory and its dimensions, we return to the central insight. The universe may be far stranger and more complex than our everyday experience suggests. The familiar three dimensions of space plus time may be just the visible surface of a deeper, higher dimensional reality. And the key to understanding this reality may lie in the mathematics of tiny vibrating strings, executing their complex dances in dimensions too small for us to directly perceive. The search for experimental evidence of these hidden dimensions continues, and in the next chapter, we will explore how scientists are attempting to detect their existence. From particle accelerators to gravitational wave observatories, from precise tests of gravity at small distances to astronomical observations of the cosmic microwave background, the hunt for signs of extra dimensions encompasses some of the most sophisticated experiments ever devised. Though the dimensions themselves may be hidden, their effects may yet reveal themselves to our increasingly sensitive instruments. For now, we carry forward the profound insight of string theory, that the architecture of reality may include dimensions beyond those we directly perceive, and that these hidden dimensions may hold the key to unifying our understanding of the fundamental forces of nature. The universe, it seems, may be even more extraordinary than we imagined. Imagine our entire universe, with its billions of galaxies stretching across billions of light years, as nothing more than a thin membrane floating in a much larger, higher dimensional space. This is the provocative picture suggested by brain world theories, one of the most intriguing developments to emerge from the study of extra dimensions. In this chapter, we'll explore how these theories reimagine our universe as a slice of a much grander reality, and examine their implications for our understanding of cosmic mysteries. The concept of brains, short for membranes, emerged from the development of string theory. Initially, string theory focused on one-dimensional objects, strings, as the fundamental constituents of reality. But as the theory evolved, particularly with the advent of M-theory in the mid-1990s, it became clear that higher dimensional objects were also essential elements of the theoretical framework. A one-brain, or string, is a one-dimensional object. A two-brain is a two-dimensional membrane, like a sheet. A three-brain is a three-dimensional volume, and the pattern continues to higher dimensions. Our universe, with its three dimensions of space and one of time, could be understood as a kind of three-brain embedded in a higher dimensional bulk space. This vision of our universe as a brain within a higher dimensional space was developed into detailed models in the late 1990s by several physicists, including Lisa Randall and Raman Sundram, Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali. Their work transformed what had been abstract theoretical concepts into models with specific, potentially testable consequences. The central insight of brain world scenarios is that different forces and particles might be confined to a brain, while others might propagate through the larger bulk space. In the most widely studied models, the electromagnetic, strong and weak nuclear forces, along with the matter particles they affect, are confined to our brain. But gravity can extend into the extra dimensions of the bulk. This seemingly simple assumption has profound implications. One of the most long-standing puzzles in physics is the enormous disparity between the strength of gravity and the other fundamental forces. The electromagnetic force between two protons, for instance, is roughly 10 to the 36th power times stronger than the gravitational force between them. This vast difference, known as the hierarchy problem, has no explanation in conventional physics. Brain world theories offer an elegant solution. If gravity alone can spread into the extra dimensions, while the other forces are confined to our brain, then gravity would naturally appear weaker from our perspective. The gravitational force would be diluted as it spreads into dimensions we cannot directly access. To visualize this, imagine two people standing on opposite sides of a lake, each holding a flashlight. One flashlight emits light in all directions, including up into the air and down into the water. The other emits light that can only travel along the surface of the lake. To an observer floating on the lake's surface, the second flashlight would appear much brighter than the first, because all of its light remains on the surface rather than spreading into the extra dimensions of air and water. Similarly, forces confined to our brain would appear stronger than gravity, which dissipates into the higher dimensional bulk. This simple geometrical explanation for one of the most puzzling aspects of fundamental physics illustrates the explanatory power of brain-world scenarios. The Randall-Sundrum model, named after its creators, introduces another key concept: the warping of extra dimensions. In this model, the extra dimension is not flat, but curved or warped. This warping causes the effective strength of gravity to vary at different locations in the extra dimension. At certain points in the higher dimensional space, gravity could be as strong as the other forces, but at our location on a brain, it appears drastically weakened. This warping also provides a mechanism for confining gravity primarily to our brain despite its ability to propagate into the bulk. The geometry of the extra dimension can act like a gravitational well, ensuring that gravity, while not strictly confined to our brain, is nonetheless concentrated there. This helps explain why we haven't observed gravitational effects from parallel brains that might exist in the same higher dimensional space. The large extra dimensions model, proposed by Arkani Hamed, Dimopoulos, and Diwali, takes a different approach. It suggests that the extra dimensions might be much larger than the Planck length, perhaps as large as a millimeter, but we still don't notice them because all the standard model particles and forces are confined to our brain. Only gravity can extend into these relatively large extra dimensions. These different brain world scenarios make different predictions about how gravity should behave at very small distances. If there are large extra dimensions, gravity's strength should increase more rapidly than expected as distances decrease below the size of these extra dimensions. Precision experiments that test gravity at the sub-millimeter scale can potentially detect such deviations from the inverse square law. Beyond offering solutions to the hierarchy problem, brain-world theories open up new possibilities for understanding cosmology, the origin and evolution of our universe. One of the most speculative but intriguing ideas is that the Big Bang itself might represent a collision between brains. In the ekpyrotic scenario, proposed by Paul Steinhardt, Neil Turok, and others, our universe began not with a singular explosion from a point of infinite density, but with the collision of two brains floating in a higher dimensional space. The energy of this collision manifested as the hot, dense, rapidly expanding state that we traditionally associate with the Big Bang. This brain collision model addresses some of the puzzling features of the early universe that are typically explained by cosmic inflation, a theorized period of exponential expansion in the first fraction of a second after the Big Bang. Both inflation and the ekpyrotic scenario can explain why the universe appears flat and why the cosmic microwave background radiation is so uniform across the sky, but they do so through different mechanisms. The ekpyrotic model suggests that the uniform conditions existed before the collision, while inflation proposes that an extremely rapid expansion smoothed out any initial irregularities. Both approaches have their theoretical challenges, but the ekpyrotic model demonstrates how brain-world scenarios can lead to entirely new ways of thinking about the most fundamental questions in cosmology. Another intriguing implication of brain-world theories concerns the nature of dark matter and dark energy, two of the most mysterious components of our universe. Dark matter, which does not emit or absorb light, but exerts gravitational pull, makes up about 85% of the matter in the universe. Dark energy, a still more enigmatic phenomenon, appears to be driving the accelerating expansion of the universe. In some brain world scenarios, dark matter could consist of ordinary matter on a parallel brane. We would not see this matter through electromagnetic interactions because light cannot travel between branes, but we would feel its gravitational effects because gravity propagates through the bulk. Similarly, dark energy might represent the gravitational influence of objects or dynamics in the bulk or on other branes. The cyclic universe model, a further development of the ekpyrotic scenario, proposes that brane collisions occur repeatedly, with each collision creating conditions similar to the Big Bang. This would mean our universe goes through endless cycles of expansion and contraction, with each cycle lasting perhaps 1 trillion years. This offers an alternative to both the traditional Big Bang theory, which proposes a singular beginning to time, and the steady-state theory, which suggests the universe has always existed in roughly its current form. Brane world scenarios also suggest new ways of thinking about fundamental physical constants. If our universe is one of many branes, perhaps with different physical laws, this could help explain why the constants of nature in our universe seem finely tuned to allow for the existence of complexity and life. Rather than requiring a designer or an incredibly fortunate accident, this fine-tuning might reflect a kind of cosmic selection effect. Among many branes with different physical laws, we naturally find ourselves in one compatible with our existence. This connects to broader ideas about the multiverse, the hypothesis that our universe is one of many, perhaps infinitely many, universes with different physical properties. Brane world theories provide one potential mechanism for how such a multiverse might be structured, with different branes representing different universes, perhaps separated from each other along extra dimensions. While these ideas are speculative, they illustrate how brane world theories have expanded the conceptual toolkit of theoretical physics, opening up new approaches to long-standing problems and suggesting new questions that might not have been formulated without the framework of extra dimensions. The experimental search for evidence of brane worlds continues along several fronts. Particle accelerators like the Large Hadron Collider search for missing energy in collisions that might indicate particles escaping into extra dimensions, or for microscopic black holes that could form if gravity becomes stronger at small distances. Precision tests of gravity at small scales look for deviations from the inverse square law that could signal the influence of extra dimensions, and cosmological observations of the cosmic microwave background and the distribution of galaxies provide constraints on models of the early universe, including those inspired by brane world scenarios. So far, no definitive evidence for brane worlds or extra dimensions has been found. The Large Hadron Collider has not detected particles escaping into extra dimensions or microscopic black holes. Precision tests of gravity have confirmed Newton's inverse square law down to distances of about 1/100th of a millimeter. And cosmological observations, while revealing puzzles like dark matter and dark energy, have not provided clear support for specific brane world models. However, these null results do not rule out brane world scenarios. They simply constrain the possible properties of the extra dimensions and branes. The extra dimensions might be smaller than current experiments can probe, or the energy required to excite modes in these dimensions might be higher than current accelerators can achieve. The search continues, with more sensitive experiments and observations potentially capable of detecting more subtle signatures of extra dimensions. Even without direct experimental confirmation, brane world theories have already transformed our understanding of what is physically and mathematically possible. They have shown how the familiar four-dimensional space-time of our experience might be embedded in a richer, higher dimensional reality. They have suggested new solutions to long-standing problems in physics, from the weakness of gravity to the origin of the universe. And they have stimulated new experimental and observational approaches to testing the limits of our current understanding. Perhaps most profoundly, brane world theories have challenged our intuitive notion that the reality we perceive directly must be all that exists. They remind us that our senses and our measuring devices have limitations, and that mathematics and theoretical insight can sometimes point to aspects of reality that lie beyond our immediate perception. The idea that our entire universe might be a brain floating in a higher dimensional space represents one of the most dramatic shifts in our cosmic perspective, since we recognized that the Earth is not the center of the solar system, or that our galaxy is one among billions. It suggests that even the vast cosmos revealed by our most powerful telescopes might be just one domain within a much larger and more complex reality. As we contemplate this possibility, we are reminded of the words attributed to Arthur Stanley Eddington. Not only is the universe stranger than we imagine, it is stranger than we can imagine. Brain world theories push the boundaries of our imagination, asking us to envision realities beyond the dimensions of our direct experience. Whether these theories ultimately prove correct in detail or not, they have already expanded our conception of what might constitute physical reality. The quest to understand the true nature of our universe, including the possibility that it might be a brain in a higher dimensional space, continues. It is a quest that combines mathematical analysis, theoretical insight, experimental ingenuity, and philosophical reflection. And it is a quest that reminds us of the remarkable human capacity to comprehend realities that extend far beyond our immediate sensory experience. As we move forward to the next chapter, we will explore how scientists are attempting to detect these hidden dimensions, examining the experimental strategies and technological innovations that might reveal the true dimensionality of our universe. The dimensions themselves may be hidden, but their effects on our four-dimensional world might yet be discerned by our increasingly sophisticated methods of observation and analysis. If extra dimensions exist beyond the familiar 3 dimensions of space and 1 of time, how might we detect them? This question lies at the heart of transforming theoretical speculations about hidden dimensions into testable scientific hypotheses. In this chapter, we explore the ingenious experimental approaches that scientists are using in their quest to find evidence of dimensions that may be hidden from our direct perception, but nevertheless influence the physical world in detectable ways. The challenge of detecting extra dimensions is formidable. If, as most theories suggest, these dimensions are compactified or curled up at scales approaching the Planck length, roughly 10 to the negative 35 meters. They would be far smaller than anything we can directly probe with current technology. For comparison, the smallest distances currently accessible in particle accelerators are about 10 to the negative 19 meters, still 16 orders of magnitude larger than the Planck length. Nevertheless, physicists have identified several potential signatures that might reveal the existence of extra dimensions indirectly. These fall into several categories: high-energy particle collisions, precise measurements of gravity at small distances, astrophysical and cosmological observations, and searches for unusual patterns in the cosmic microwave background radiation. Let us begin with high-energy particle accelerators, the most powerful tools humans have built for probing the fundamental structure of matter. The Large Hadron Collider near Geneva, Switzerland, accelerates protons to nearly the speed of light and collides them with energies reaching 13 trillion electron volts. These collisions create conditions similar to those that existed a fraction of a second after the Big Bang, allowing physicists to study particles and forces in extreme conditions. If extra dimensions exist and are large enough, some intriguing phenomena might occur in these high-energy collisions. One possibility is the production of Kaluza-Klein modes, particles that correspond to waves propagating through the extra dimensions. In our 3-dimensional world, these would appear as heavier versions of known particles, with masses determined by the size of the extra dimensions. Just as a vibrating guitar string produces harmonics at specific frequencies, particles moving through compactified extra dimensions would have energy states at specific values. Another potential signature is missing energy in particle collisions. If some of the energy from a collision escaped into extra dimensions, detectors would record less energy than the initial collision should have produced. This missing energy could signal particles traveling into dimensions inaccessible to our measuring devices. Perhaps the most dramatic possibility is the creation of microscopic black holes. In conventional physics, creating a black hole in a particle accelerator would require concentrations of energy far beyond what current technology can achieve. But if extra dimensions exist, gravity might become much stronger at very small distances, making it possible to create tiny black holes at energies within reach of the Large Hadron Collider. These microscopic black holes would not pose any danger to Earth. They would evaporate almost instantly via Hawking radiation, leaving behind a distinctive pattern of particles that detectors could identify. The detection of such micro-black holes would provide compelling evidence not only for extra dimensions, but also for the correctness of Hawking's theoretical prediction of black hole radiation, which has never been directly observed. So far, the Large Hadron Collider has not found clear evidence for extra dimensions. No Kaluza-Klein modes, unexplained missing energy, or microscopic black holes have been definitively detected. However, these null results do not rule out extra dimensions. They simply constrain the possible sizes and properties of such dimensions. The extra dimensions might be smaller than those that would produce observable effects at current accelerator energies, or the specific models being tested might not accurately represent the actual structure of the extra dimensions if they exist. Future accelerators with even higher energies might probe deeper into these possibilities. Proposed facilities like the Future Circular Collider or the Compact Linear Collider could potentially reach energies several times higher than the Large Hadron Collider, expanding the range of extra-dimensional models that could be tested experimentally. A second approach to detecting extra dimensions involves precise measurements of gravity at small distances. According to Newton's law of gravity, the force between two masses is inversely proportional to the square of the distance between them. This inverse square law has been confirmed over an enormous range of distances, from astronomical scales down to about 1/100th of a millimeter. However, if extra dimensions exist, the behavior of gravity might deviate from the inverse square law at distances comparable to the size of these extra dimensions. This is because at distances smaller than the size of an extra dimension, gravity would spread out in more than 3 spatial dimensions, changing its dependence on distance. To test this possibility, physicists have developed incredibly sensitive experiments to measure gravitational forces between objects separated by very small distances. One approach uses torsion balances, instruments consisting of small masses suspended on a rotating apparatus that can detect tiny torques caused by gravitational attraction. Another uses microscopic cantilevers whose movements can be measured with exquisite precision. These experiments are extraordinarily challenging. At small distances, electromagnetic forces between objects are much stronger than gravity and must be carefully shielded or accounted for. Vibrations from the environment must be isolated, and thermal effects must be controlled. Despite these challenges, researchers have pushed measurements of the gravitational inverse square law down to distances of about 10 micrometers, or 1/100th of a millimeter. So far, these experiments have found no deviations from the inverse square law, placing upper limits on the size of any extra dimensions. If extra dimensions exist, they must be smaller than the distances these experiments can probe. Again, this does not rule out the existence of extra dimensions, but constrains their possible properties. A third approach looks to the cosmos for signs of extra dimensions. Astrophysical observations of phenomena like supernovae, neutron stars, and black holes can provide information about how gravity behaves under extreme conditions, potentially revealing the effects of extra dimensions. For instance, if gravity leaks into extra dimensions, stellar objects might cool faster than expected as they emit gravitational radiation into these dimensions. This could affect the observed properties of supernovae and neutron stars. Similarly, black holes might evaporate faster due to gravitational radiation into extra dimensions, altering their expected lifetimes and observable signatures. The recent detection of gravitational waves, ripples in space-time caused by violent cosmic events like black hole mergers, opens a new window for testing theories of extra dimensions. Some models predict that gravitational waves might oscillate into extra dimensions and back, causing detectable modulations in the signals received by observatories like LIGO and Virgo. Other models suggest that the speed of gravitational waves might differ slightly from the speed of light in ways that depend on the structure of the extra dimensions. The observation of the neutron star merger GW 170817, detected both in gravitational waves and in electromagnetic radiation, has already placed constraints on some theories of extra dimensions by confirming that gravitational waves and light travel at the same speed to a very high precision. Future gravitational wave observations with even greater sensitivity might reveal subtle effects that could signal the presence of extra dimensions. Cosmological observations provide yet another avenue for testing theories of extra dimensions. The cosmic microwave background radiation, the afterglow of the Big Bang that permeates the universe, contains tiny temperature fluctuations that encode information about the early universe. The precise pattern of these fluctuations depends on the physics that operated during cosmic inflation, the theorized period of rapid expansion in the first fraction of a second after the Big Bang. Some models of extra dimensions predict specific signatures in the cosmic microwave background, such as particular patterns of polarization or statistical properties of the temperature fluctuations. The increasingly precise measurements of the cosmic microwave background by satellites like Planck and ground-based telescopes allow these predictions to be tested. Similarly, the large-scale structure of the universe, the distribution of galaxies and galaxy clusters across space, carries information about the fundamental physics that governed cosmic evolution. If extra dimensions influence the expansion history of the universe or the growth of cosmic structures, their effects might be discernible in surveys of the distribution of matter across vast cosmic distances. Beyond these established approaches, researchers continue to explore innovative ways to detect extra dimensions. One intriguing possibility involves testing whether the fundamental constants of nature, quantities like the fine structure constant that determines the strength of the electromagnetic force, vary over cosmic time or across different regions of space. Some theories of extra dimensions predict such variations, which might be detected through precise spectroscopic observations of distant quasars or through laboratory experiments comparing different types of atomic clocks. Another approach examines whether neutrinos, nearly massless particles that rarely interact with ordinary matter, might travel partly through extra dimensions. This could cause them to appear and disappear in our three-dimensional space in a distinctive pattern. Experiments like IceCube at the South Pole, which detects neutrinos passing through a cubic kilometer of ice, might be sensitive to such effects. Researchers are also exploring connections between theories of extra dimensions and quantum information theory. Some propose that quantum entanglement, the spooky connection between particles that Einstein called spooky action at a distance, might be explained through connections in higher dimensions. Experiments testing the fundamental nature of quantum entanglement could potentially reveal clues about the structure of space-time and the existence of extra dimensions. The search for extra dimensions exemplifies the interplay between theory and experiment that drives physics forward. Theoretical insights suggest possible signatures of extra dimensions, which in turn inspire new experimental approaches. The results of these experiments, whether positive or negative, refine the theories and guide the development of new models, which then suggest new experimental tests. This iterative process gradually narrows the range of possibilities, either eventually detecting extra dimensions or placing increasingly stringent constraints on their properties. It's worth noting that the absence of clear evidence for extra dimensions to date does not mean they don't exist. The history of physics is filled with cases where phenomena existed but remained undetected until the right experimental approach was developed. The neutrino was proposed in 1930 to explain certain observations in radioactive decay, but was not directly detected until 1956. The Higgs boson was theoretically predicted in 1964, but not detected until 2012 at the Large Hadron Collider. Gravitational waves were predicted by Einstein in 1916, but not directly observed until 2015 by LIGO. Similarly, extra dimensions might exist but remain hidden because they are too small, too weakly coupled to our observable world, or manifest in ways we have not yet learned to recognize. The absence of evidence is not evidence of absence, particularly when dealing with phenomena that might operate at scales far removed from our everyday experience. Moreover, even if extra dimensions exist exactly as current theories propose, detecting them might require technologies beyond our current capabilities. Just as the detection of the Higgs boson required the construction of the Large Hadron Collider, a $13 billion facility and one of the most complex machines ever built, the definitive detection of extra dimensions might require even more advanced instruments. Some physicists speculate that a conclusive test of theories involving extra dimensions might require energies approaching the Planck scale, where quantum gravity effects become dominant. Achieving such energies in a controlled laboratory setting would be far beyond current technology. However, natural cosmic processes might provide windows into these extreme energy scales. Ultra-high energy cosmic rays, particles from space with energies millions of times higher than those achievable in the Large Hadron Collider, might reveal physics at scales closer to the Planck energy. Similarly, the early universe, particularly during the inflationary epoch, involved energies far higher than we can recreate on Earth, making cosmological observations a crucial testing ground for theories of extra dimensions. The challenge of detecting hidden dimensions reminds us of the fundamental limitations of human perception and the power of mathematics and scientific instrumentation to transcend these limitations. We cannot directly see, hear, or touch dimensions beyond the familiar 3 of space and 1 of time. But through mathematical theories, sophisticated experiments, and observations of the cosmos, we can probe the possible existence of dimensions that lie beyond our immediate sensory experience. This pursuit also raises profound philosophical questions about the nature of scientific knowledge and the relationship between mathematics, empirical observation, and physical reality. How should we regard theoretical entities like extra dimensions that are mathematically elegant and help resolve theoretical problems, but remain experimentally unverified? At what point does a theory, with increasingly remote prospects for experimental confirmation, cease to be scientific? These questions have no simple answers and continue to be debated among physicists and philosophers of science. What is clear is that the search for extra dimensions has already enriched our understanding of the fundamental principles that might govern the universe at its deepest levels. Whether or not hidden dimensions ultimately prove to exist in the form currently theorized, the intellectual journey of exploring their possibility has led to profound insights in theoretical physics, cosmology, and mathematics. As we look to the future, the quest to detect hidden dimensions continues on multiple fronts. New particle accelerators, more sensitive gravitational wave detectors, more precise cosmological observations, and innovative tabletop experiments will push the boundaries of our knowledge further. Perhaps one of these approaches will finally reveal conclusive evidence of dimensions beyond the familiar 4 of space-time. Or perhaps new theoretical insights will reshape our understanding of the problem, suggesting different experimental signatures to look for, or even different conceptual frameworks for thinking about the dimensionality of reality. Whatever the ultimate outcome, the search for hidden dimensions exemplifies science at its most ambitious, attempting to unveil aspects of reality that lie beyond our direct perception, but might nevertheless be crucial to the fundamental workings of the universe. It is a search that connects the mathematical abstractions of theoretical physics to concrete experimental techniques and technological innovations, all in service of answering one of the most basic questions we can ask about the nature of the world: how many dimensions does reality have? As we move to the next chapter, we will explore the profound implications that the existence of extra dimensions would have for our understanding of physics and cosmology. From resolving long-standing puzzles like the hierarchy problem, to providing new perspectives on dark matter and dark energy. From suggesting novel approaches to quantum gravity, to offering potential explanations for the apparent fine-tuning of physical constants, the concept of hidden dimensions has far-reaching consequences for our scientific worldview. Whether these dimensions ultimately prove to be physical realities or useful mathematical constructs, they have already transformed how physicists think about the fundamental structure of the universe. If extra dimensions truly exist beyond the familiar three dimensions of space and one of time, their implications for our understanding of physics and cosmology would be profound. Whether they remain purely theoretical constructs or are eventually confirmed experimentally, the concept of hidden dimensions has already transformed how scientists think about fundamental questions regarding the nature of reality, the origin of the universe, and the ultimate fate of the cosmos. In this chapter, we explore the far-reaching consequences that hidden dimensions would have for our scientific worldview. Perhaps the most immediate implication concerns the unification of the fundamental forces of nature. Since the time of Einstein, physicists have dreamed of finding a unified theory that would bring together all the known forces, gravity, electromagnetism, and the strong and weak nuclear forces under a single mathematical framework. Extra dimensions offer a geometric path toward this unification. In Kaluza-Klein theory, the prototype for all higher dimensional theories, the addition of a fifth dimension allowed gravity and electromagnetism to be unified as aspects of a single five-dimensional gravitational field. Modern theories like string theory extend this insight, suggesting that all four fundamental forces might be unified in a higher dimensional space. What appear to us as distinct forces in our four-dimensional space-time would be revealed as different aspects of a single, more fundamental interaction in the full, higher dimensional reality. This geometric unification would represent a profound simplification in our understanding of nature. Instead of a collection of separate forces with seemingly arbitrary strengths and properties, we would have a single underlying principle from which the apparent complexity of our world emerges. The diversity of particles and forces in our four-dimensional experience would reflect the way the higher dimensional reality is structured and compactified, just as the variety of notes that can be played on a violin string reflect its length, tension, and the patterns in which it vibrates. A second major implication concerns the hierarchy problem, the puzzle of why gravity is so much weaker than the other fundamental forces. As we discussed in earlier chapters, brain-world scenarios suggest that gravity might only appear weak in our three-dimensional world because it spreads into extra dimensions, diluting its strength from our perspective. Meanwhile, the other forces remain confined to our three-brain. If confirmed, this explanation would resolve one of the most perplexing questions in fundamental physics: the enormous disparity between the gravitational force and the other forces, a factor of roughly 10 to the 36th power, would no longer be an unexplained mystery, but a natural consequence of the geometric structure of the higher dimensional space in which our universe is embedded. Extra dimensions also offer new perspectives on the cosmological constant problem. Observations indicate that our universe is expanding at an accelerating rate, driven by what we call dark energy. In quantum field theory, the vacuum energy that permeates empty space should contribute to this acceleration. However, theoretical calculations of this vacuum energy yield values that are too large, by a factor of 10 to the 120, perhaps the most extreme disagreement between theory and observation in all of science. Some models involving extra dimensions suggest that the cosmological constant, which determines the vacuum energy density, might be nearly cancelled by effects related to the geometry or dynamics of the extra dimensions. For instance, in certain brain-world scenarios, the positive vacuum energy in our universe might be mostly cancelled by negative energy associated with the curvature of the bulk space or with other branes. These approaches have not yet yielded a complete solution to the cosmological constant problem, but they open new avenues for investigation that were not available in purely four-dimensional theories. The sheer size of the discrepancy between theoretical expectations and observations suggests that something fundamental is missing from our current understanding, and extra dimensions might provide a crucial piece of the puzzle. Extra dimensions also offer novel explanations for dark matter, the mysterious substance that makes up roughly 85% of the matter in the universe, but does not emit or absorb light. In some brain world scenarios, dark matter could consist of ordinary matter on a parallel brane. We would not see this matter through electromagnetic interactions, because light is confined to individual brains. But we would feel its gravitational effects because gravity propagates through the bulk space between brains. Alternatively, dark matter might consist of Kaluza-Klein excitations, particles that possess momentum in the extra dimensions and appear as massive particles in our four-dimensional world. Such particles would interact with ordinary matter only through gravity and possibly the weak force, matching the known properties of dark matter. Similarly, some theories propose that dark energy, which drives the accelerating expansion of the universe, might represent the influence of extra dimensions on our four-dimensional space-time. It could reflect the dynamics of the bulk space or the interaction between different brains within this higher dimensional reality. While these explanations remain speculative, they illustrate how the concept of extra dimensions provides new tools for addressing some of the most challenging problems in contemporary cosmology. The nature of dark matter and dark energy, which together constitute about 95% of the energy content of the universe, might ultimately be understood in terms of higher dimensional physics. Extra dimensions also have profound implications for our understanding of black holes and their properties. In conventional four-dimensional physics, black holes are completely characterized by just three parameters: their mass, electric charge, and angular momentum. This property, known as the no-hair theorem, means that all other information about what falls into a black hole is lost, at least from the perspective of an outside observer. However, in higher dimensional theories, black holes can have additional properties related to the extra dimensions. They might carry charges or currents associated with fields that exist in the higher dimensional space, but are not visible in our four-dimensional world. The thermodynamic properties of black holes, including their entropy and the rate at which they emit Hawking radiation, would also be modified by the presence of extra dimensions. More exotic possibilities emerge as well. In some brain world scenarios, microscopic black holes might be able to escape our brain, leaking into the bulk space between brains. Conversely, black holes from other brains might occasionally cross into our universe, potentially producing distinctive astrophysical signatures. String theory provides even more elaborate black hole physics. Certain types of black holes in string theory can be precisely mapped to systems of vibrating strings, providing a detailed microscopic account of black hole entropy. This represents one of the major achievements of string theory, explaining the thermodynamic properties of black holes that were first discovered by Stephen Hawking through semi-classical calculations. The implications extend to the interior of black holes as well. The singularities at the centers of black holes, where general relativity predicts that space and time become infinitely curved, have long been considered a sign that the theory breaks down. Extra-dimensional theories suggest that these singularities might be resolved when the full, higher dimensional physics is taken into account. What appears as a singular point in our four-dimensional description might be a more well-behaved extended object in the full higher dimensional space. Beyond black holes, extra dimensions could influence the very beginning and the ultimate fate of our universe. In cyclic or ekpyrotic models, as we explored in the previous chapter, the Big Bang is reinterpreted not as the absolute beginning of time, but as a collision between brains in a higher dimensional space. This collision would not be a singular event, but one instance in an eternal cycle of brain collisions, each initiating a new cosmic epoch. This perspective transforms our understanding of cosmic history. Instead of a single universe with a definite beginning at the Big Bang, we might inhabit one cycle in an eternal process, with each cycle lasting perhaps 1 trillion years before the next collision occurs. The apparent beginning of time associated with the Big Bang would be an artifact of our limited four-dimensional perspective, with the true history of reality extending infinitely into the past within the higher dimensional bulk. Similarly, the ultimate fate of our universe might be determined by dynamics in the extra dimensions. In conventional cosmology, the future of the universe depends on the balance between the expansion, driven by the Big Bang, and the gravitational pull of matter, with dark energy adding an accelerating component to the expansion. In brane-world scenarios, additional factors come into play, such as the attraction between branes in the higher dimensional bulk, or the dynamics of the bulk space itself. Some models predict that after trillions of years of expansion, our brane might be drawn toward another brane, eventually colliding and initiating a new cycle. Others suggest that the expansion might continue forever, with the fate of our universe decoupled from what happens in the larger bulk space. The range of possibilities is far richer than in purely four-dimensional cosmologies. Extra dimensions also have implications for the fundamental constants of nature, quantities like the fine structure constant, which determines the strength of the electromagnetic force, or the ratios between the masses of elementary particles. In conventional physics, these constants must be measured experimentally and inserted into our theories by hand. There is no explanation for why they have the specific values they do. In theories with extra dimensions, particularly string theory, these constants are not truly fundamental, but emerge from the geometry and topology of the extra dimensions. The specific way in which the extra dimensions are compactified, folded, or curled up determines the values of the constants we observe in our four-dimensional world. This raises the tantalizing possibility that the fundamental constants are not arbitrary, but are determined by the requirement of mathematical consistency in the higher dimensional theory. However, it also introduces a challenge. As current understanding suggests, there might be an enormous landscape of possible configurations for the extra dimensions, each corresponding to a different set of physical constants. This vast landscape of possibilities has led to anthropic arguments. The idea that we observe the specific values we do because they allow for the existence of complex structures, including life, a topic we will explore more deeply in later chapters. The concept of extra dimensions also inspires new approaches to quantum gravity, the elusive theory that would reconcile quantum mechanics with general relativity. In conventional attempts to quantize gravity, mathematical infinities appear that cannot be eliminated using the standard techniques of renormalization that work for the other forces. These infinities have been a persistent obstacle to developing a consistent quantum theory of gravity. Theories with extra dimensions offer potential solutions to this problem. In string theory, the extended nature of strings smooths out the point like interactions that lead to infinities in conventional approaches. The graviton, the hypothetical particle that carries the gravitational force, emerges as a particular vibrational mode of the string, and its interactions are naturally well behaved. Similarly, in some brane-world scenarios, gravity behaves differently at very small distances due to the influence of extra dimensions. This modified high-energy behavior can ameliorate the mathematical difficulties of quantum gravity. For instance, in the Randall-Sundrum model, the warping of the extra dimension provides a natural cutoff that might regulate the otherwise problematic high-energy behavior of gravity. Beyond these technical advantages, extra-dimensional theories provide conceptual frameworks for thinking about quantum gravity that were not available in purely four-dimensional approaches. The ADS-CFT correspondence, for example, proposes a precise mathematical equivalence between a gravitational theory in a higher dimensional space and a quantum field theory without gravity on the boundary of that space. This powerful duality has provided insights into quantum aspects of black holes, holography, and the emergence of space-time from more fundamental quantum mechanical principles. The holographic principle, the idea that all the information contained in a volume of space can be represented on the boundary of that region, finds its most precise realization in the context of extra-dimensional theories. What appears to us as a three-dimensional reality might be encoded on a two-dimensional surface, with the third dimension of space and the dimension of time emerging from this more fundamental description. This represents a profound reimagining of the nature of space and time, suggesting that dimensions themselves might be emergent rather than fundamental. Extra dimensions also have implications for our understanding of symmetry in physics. Symmetries, patterns that remain unchanged under certain transformations, have played a central role in the development of modern physics. The Standard Model of particle physics is essentially a theory of symmetries and their breaking. In theories with extra dimensions, new types of symmetries become possible based on the geometry and topology of the higher dimensional space. These include Kaluza-Klein symmetries associated with the shape of the extra dimensions, and dualities that relate seemingly different physical theories as manifestations of the same underlying higher dimensional reality. T-duality in string theory, for instance, relates a theory compactified on a circle of radius r to another theory compactified on a circle of radius 1 over r, revealing a profound symmetry between large and small dimensions. Similarly, mirror symmetry relates string theories compactified on different Calabi-Yau manifolds, providing powerful mathematical tools for exploring the landscape of possible extra-dimensional geometries. These exotic symmetries not only enrich our theoretical understanding, but have led to practical advances in mathematics, including solutions to long-standing problems in enumerative geometry. The interplay between physics and mathematics has been one of the most fruitful aspects of research on extra dimensions, with insights flowing in both directions. As we conclude this exploration of the implications of extra dimensions for physics and cosmology, we return to a central theme. If extra dimensions exist, our current understanding of the universe is radically incomplete. The theories we have developed based on four-dimensional spacetime would be approximations, valid at the scales and energies we have been able to probe, but breaking down when the full higher dimensional reality becomes significant. This might explain why we have been unable to formulate a fully consistent quantum theory of gravity, or to explain the values of fundamental constants. We have been working with an incomplete picture, missing crucial aspects of reality that are only visible when all dimensions are taken into account. Whether extra dimensions ultimately prove to be physical realities or useful mathematical constructs, the concept has already transformed how physicists think about the fundamental questions of their discipline. It has provided new approaches to long-standing problems, suggested novel experimental signatures to search for, and expanded our conception of what might constitute the fundamental nature of reality. In the next chapter, we will explore the philosophical and existential questions raised by the possibility of hidden dimensions. What would it mean for our understanding of reality if dimensions exist beyond those we directly perceive? How would it affect our place in the cosmos? And what might it tell us about the limits of human knowledge and the reach of the human imagination? Beyond the mathematical formulations and experimental predictions, the concept of hidden dimensions raises profound philosophical and existential questions about the nature of reality and our place within it. What does it mean if the universe contains dimensions that we cannot directly perceive? How should we understand a reality that extends beyond the boundaries of our sensory experience? And what might these hidden aspects of the cosmos tell us about the human condition and our quest to comprehend the universe? Let us begin with perhaps the most fundamental philosophical question raised by the possibility of extra dimensions, the relationship between appearance and reality. Throughout history, philosophers have distinguished between the world as it appears to us and the world as it might truly be in itself. From Plato's allegory of the cave, where prisoners mistake shadows for reality, to Kant's distinction between phenomena and noumena, this tension between appearance and underlying reality has been a persistent theme in human thought. The concept of hidden dimensions gives this ancient philosophical question a concrete scientific form. If extra dimensions exist, then the three-dimensional world we perceive would be just a slice or projection of a higher dimensional reality. Our perceptual apparatus, evolved to navigate a macroscopic world of three spatial dimensions, would be revealing only a partial view of what exists. The true nature of reality would extend beyond what our senses can directly apprehend. This possibility challenges us to reconsider what we mean by reality. Is reality limited to what we can perceive or measure directly? Or does it include aspects that might be inferred through mathematical reasoning and indirect experimental evidence? The history of science suggests the latter. Atoms were posited based on theoretical reasoning long before they could be observed, and today we routinely accept the existence of entities like quarks or quantum fields that are known only through their mathematical descriptions and indirect effects. Extra dimensions would represent an extension of this pattern, entities posited based on mathematical consistency and indirect evidence rather than direct observation. But they would be unusual in representing not just new kinds of objects within our familiar spacetime, but additional aspects of spacetime itself. They would constitute not just new things to be discovered, but new dimensions of discovery. This leads to a second philosophical question: the limits of human knowledge and understanding. Can we truly comprehend a reality that extends beyond the dimensions of our direct experience? The mathematician and philosopher William Kingdon Clifford addressed this question in 1870 in an essay titled The Philosophy of the Pure Sciences, writing, "I hold that we can think of the world in terms of space of 4 dimensions, but we cannot perceive it as such." Clifford's insight remains relevant today. We can mathematically describe spaces of 10, 11, or even 26 dimensions. We can analyze their properties, calculate how fields would propagate through them, and derive predictions for how their existence might manifest in our 4-dimensional experience. But we cannot form mental images or direct intuitions of these higher dimensional spaces in the same way we can visualize 3-dimensional objects. This limitation of our intuition is not necessarily a limitation of our knowledge. We routinely work with mathematical concepts that defy direct visualization, from complex numbers to Hilbert spaces of infinite dimensions. The mathematics of extra dimensions may be complex, but it is not in principle beyond human comprehension. What we cannot picture, we can still understand through mathematical reasoning and analogy. Indeed, the history of physics shows a progressive abstraction from direct sensory experience. Newton's laws of motion and gravity could be readily visualized and connected to everyday experience. Maxwell's equations of electromagnetism required more mathematical sophistication, but still described fields that could be represented visually. Quantum mechanics and general relativity pushed further into mathematical abstraction, describing realities that defy simple visualization. Extra dimensions represent a further step in this direction, challenging us to comprehend reality through mathematics, even when it extends beyond what we can directly imagine. A third philosophical question concerns the role of mathematics in describing reality. The physicist Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in the natural sciences. The surprising ability of mathematical structures originally developed for their intrinsic interest to describe the physical world with remarkable precision. Theories of extra dimensions exemplify this mysterious connection between mathematics and physical reality. The mathematical exploration of higher dimensional spaces predates their application in physics. When physicists like Kaluza and Klein discovered that adding an extra dimension to Einstein's equations naturally incorporated electromagnetism, they were drawing on mathematical structures that had been developed for purely abstract purposes. Similarly, the Calabi-Yau manifolds that feature prominently in string theory were first studied as abstract mathematical objects. Only later was it discovered that they had exactly the properties needed to serve as the compactified extra dimensions in a potentially unified theory of physics. As the mathematician Xing-Tung Yao commented, "It is a mystery why these spaces, which were studied for their mathematical beauty, turn out to be exactly what is needed in string theory." This convergence of mathematical elegance and physical applicability raises deep questions about the nature of mathematics itself. Is mathematics a human invention, a system of abstract reasoning created by the human mind? Or is it a discovery, an exploration of structures that exist independently of human thought? And if the latter, what does it mean that the physical universe seems to embody these mathematical structures so precisely? The philosopher and mathematician Bertrand Russell captured this mystery when he wrote, "Mathematics, rightly viewed, possesses not only truth, but supreme beauty, a beauty cold and austere, like that of sculpture, without appeal to any part of our weaker nature, sublimely pure, and capable of a stern perfection, such as only the greatest art can show." Extra dimensions remind us of this sublime aspect of mathematical physics, the way it reveals patterns and structures of extraordinary beauty that extend beyond what our senses can directly apprehend. Whether these extra dimensions prove to be physical realities or useful mathematical constructs, they exemplify the power of mathematical reasoning to transcend the limitations of direct human experience. A fourth philosophical question, raised by hidden dimensions, concerns our place in the cosmos. Throughout history, scientific advances have repeatedly decentered humanity from what was once thought to be a privileged position. Copernicus showed that Earth is not the center of the universe, but one planet among several orbiting the Sun. Darwin demonstrated that humans are not separate from the animal kingdom, but emerged through the same evolutionary processes as all other species. Modern cosmology reveals that our Sun is one star among billions in our galaxy, which is itself one galaxy among billions in the observable universe. The concept of hidden dimensions potentially continues this decentering process. If our three-dimensional space is just a brain floating in a higher dimensional bulk, then even the vast cosmos revealed by our telescopes would be just one domain within a much larger and more complex reality. Our entire universe, with its billions of galaxies stretching across billions of light years, might be just a slice of a grander multi-dimensional structure. This perspective invites both humility and wonder. Humility in recognizing the limitations of our perception and the vastness of what might lie beyond our direct experience. Wonder in contemplating the extraordinary richness and complexity of a reality that continues to reveal new depths as our scientific understanding advances. Yet there is another side to this philosophical coin. While theories of extra dimensions might decenter our physical place in the cosmos, they also highlight the remarkable capacity of the human mind to transcend the limitations of sensory experience, that we can conceive of dimensions beyond those we directly perceive, develop mathematical frameworks to describe them, and devise experiments to test their existence speaks to the power of human reason to reach beyond immediate appearance toward deeper realities. In this sense, extra dimensions tell us something profound about human consciousness and its relation to the physical world. Our minds, evolved in a three-dimensional environment to solve practical problems of survival and reproduction, have somehow developed the capacity to conceptualize realities that extend far beyond our direct experience. This suggests that consciousness may be more than just a tool for navigating the macroscopic world. It may be a faculty capable of grasping fundamental aspects of reality that transcend our immediate sensory horizon. This leads to a fifth philosophical question: the relationship between science and other ways of knowing. Throughout human history, various spiritual and mystical traditions have suggested the existence of dimensions or planes of reality beyond ordinary perception. From the Buddhist concept of lokus or worlds to the Kabbalistic notion of Sephirot, from the Hindu idea of multiple cosmic planes to the Platonic realm of forms, many traditions have proposed that reality extends beyond what we directly perceive. The scientific concept of extra dimensions differs from these traditional ideas in its mathematical precision, its grounding in physical theory, and its connection to experimental testing. Yet there is an intriguing resonance between the scientific proposal that reality has hidden dimensions and these much older intuitions that the world we perceive is not all that exists. This resonance does not imply equivalence. The extra dimensions of string theory, or M theory, with their precise mathematical properties and physical implications, are very different from the spiritual dimensions or planes proposed in various wisdom traditions. But it does suggest that the human intuition that reality extends beyond immediate appearance has found expression in both scientific and spiritual contexts. Perhaps this speaks to a deep human tendency to seek what lies beyond the horizon of current understanding, to push against the boundaries of the known. Whether through scientific investigation, philosophical reflection, artistic expression, or spiritual practice, humans have consistently reached for realities that transcend immediate experience. Extra dimensions, in their scientific formulation, represent one manifestation of this perennial human quest. A sixth philosophical question concerns the nature of explanation itself. What constitutes a satisfying explanation in physics? Traditional scientific explanations often involve reducing complex phenomena to simpler, more fundamental principles. But theories of extra dimensions seem to do the opposite, explaining observed four-dimensional phenomena by postulating a more complex, higher dimensional reality. This might seem counterintuitive. How can we explain something simple by invoking something more complex? Yet on closer examination, theories of extra dimensions do follow a pattern of explanatory simplification. While they posit a reality with more dimensions, they often do so to unify previously separate forces or principles. The complexity of additional dimensions serves the goal of theoretical unification and simplification at a deeper level. In Kaluza-Klein theory, for instance, the addition of a fifth dimension allows gravity and electromagnetism to be unified as aspects of a single higher dimensional gravitational field. Similarly, in string theory, the addition of multiple extra dimensions allows all four fundamental forces to be understood as different manifestations of a single underlying dynamics of strings in higher dimensional space. This pattern suggests that explanatory power in physics does not always involve reducing the number of entities or dimensions, but may sometimes involve finding a more unified framework, even if that framework includes elements that extend beyond our direct experience. What matters is not the simplicity of the ontology, what exists, but the simplicity and coherence of the principles that govern what exists. A seventh philosophical question raised by hidden dimensions concerns the nature of space and time themselves. In our everyday experience, space and time appear to be the arena in which events occur, a fixed background against which the drama of the universe unfolds. But modern physics, particularly general relativity, has already challenged this view, showing that space and time are dynamic entities that interact with matter and energy. Theories of extra dimensions take this reconceptualization even further. In some formulations, the dimensions we experience, including time itself, might be emergent properties of a more fundamental reality, rather than basic constituents of it. The holographic principle, for instance, suggests that what appears to be a three-dimensional space might be encoded on a two-dimensional boundary, with the third spatial dimension emerging from this more fundamental description. Similarly, in certain string theory scenarios, space and time themselves might be built from more primitive constituents, perhaps strings and brains, or even more fundamental quantum entities. The dimensions we experience would then be large-scale, collective phenomena, rather than fundamental building blocks of reality. This possibility invites us to reconsider what we mean by space and time, and challenges our intuitive understanding of dimensionality itself. If dimensions can emerge from more fundamental processes, then the question of how many dimensions reality has becomes more complex. The answer might depend on the scale at which we ask the question and the theoretical framework we use to interpret it. An eighth philosophical question concerns the anthropic principle and the apparent fine-tuning of physical constants. Our universe seems remarkably well suited for the existence of complex structures, including life. The fundamental constants of nature, quantities like the strength of the electromagnetic force or the mass of the electron, fall within narrow ranges that allow for the formation of atoms, stars, and ultimately living beings. If these constants were slightly different, the universe would be incapable of supporting complexity as we know it. Theories with extra dimensions, particularly string theory with its vast landscape of possible configurations, suggest an intriguing explanation for this apparent fine-tuning. If different configurations of the extra dimensions correspond to different values of the physical constants, and if different regions of a multiverse realize different configurations, then it might not be surprising that we find ourselves in a region with constants conducive to life. We could only exist in such a region, regardless of how rare or common such regions might be in the larger multiverse. This anthropic reasoning remains controversial among physicists and philosophers. Some see it as a cop-out that abandons the traditional goal of finding unique explanations for the properties of our universe. Others view it as a natural extension of the Copernican principle, recognizing that our perspective is limited by the conditions necessary for our existence. Whatever one's view of anthropic reasoning, theories of extra dimensions have given it concrete form and connected it to potentially testable physical models. They have transformed what was once a purely philosophical speculation into a scientific hypothesis with potential empirical implications. A ninth and final philosophical question concerns the ultimate limits of human knowledge. Is there a final theory of physics that would completely describe the fundamental nature of reality? Or is our knowledge always partial and provisional, with each new theory revealing new questions and horizons? Theories of extra dimensions remind us that what appears fundamental at one level of understanding may be revealed as partial or approximate from a deeper perspective. The three dimensions of space that seem so basic to our experience might be just one manifestation of a more fundamental, higher dimensional reality. This pattern of successive revelations, raising new questions, characterizes the history of physics and suggests that our quest for understanding may have no final endpoint. As the physicist and philosopher David Bohm wrote, "What is always more than we can say. However far our knowledge extends, there is always something more, an inexhaustible depth that is not accessible to what is already known." This principle seems to be validated repeatedly as our scientific understanding advances, with each new level of explanation opening doors to further questions. Yet the remarkable success of mathematical physics in describing the natural world also suggests that human knowledge, while never complete, can progressively approximate deeper aspects of reality. The concept of hidden dimensions, whether they ultimately prove to be physical realities or useful mathematical constructs, exemplifies this paradoxical nature of scientific knowledge, always incomplete, yet always reaching toward what lies beyond the horizon of current understanding. As we reflect on these philosophical and existential questions, we are reminded that physics at its deepest level is not merely a technical enterprise, but a profound exploration of the nature of reality and our place within it. The mathematics of extra dimensions may be abstruse, the experimental evidence elusive, but the questions these theories raise touch on the most basic aspects of human existence, our quest to understand the universe and our relation to it. In the next chapter, we will explore how the concept of hidden dimensions has influenced popular culture, inspiring artistic, literary, and cinematic explorations of higher dimensional realities. From Edwin Abbott's 19th century novel Flatland to contemporary science fiction films, the idea that reality might extend beyond the dimensions of our direct experience has captured the human imagination and provided fertile ground for creative expression. The concept of hidden dimensions has captivated not only scientists and philosophers, but also artists, writers, filmmakers, and the broader public imagination. From literature to cinema, from visual art to music, the idea that reality might extend beyond the three dimensions we directly perceive has inspired creative explorations that both reflect and shape our cultural understanding of these abstract concepts. In this chapter, we explore how hidden dimensions have been portrayed in popular culture and how these portrayals have influenced public understanding of these complex scientific ideas. The story begins long before modern physics proposed the existence of extra dimensions. In 1884, Edwin Abbott, an English schoolmaster and theologian, published a remarkable novella titled Flatland, a romance of many dimensions. This slender volume, written under the pseudonym A Square, describes a two-dimensional world inhabited by geometric figures. The narrator, a square, lives in a flat plane where all residents can move only forward and backward, left and right, with no concept of up or down. The square's understanding of reality is transformed when he is visited by a sphere from the third dimension. At first, the square can perceive the sphere only as a circle that mysteriously changes size as it passes through the plane of Flatland. But when the sphere lifts the square out of his two-dimensional world, giving him a glimpse of the third dimension, the square's understanding of reality is forever changed. Abbott's tale functions simultaneously as a mathematical exploration, a social satire of Victorian hierarchy, and a philosophical meditation on the limits of perception. But most significantly for our purposes, it provides an accessible way to imagine how beings limited to fewer dimensions than our own might perceive and misperceive a higher dimensional reality. By analogy, it invites us to consider how our own three-dimensional perspective might be similarly limited, missing aspects of a higher dimensional reality that surrounds us. Flatland has remained continuously in print since its publication and has inspired numerous adaptations and extensions. In 1965, A.K. Dewdney published The Planiverse, which elaborated on the physics and biology of a two-dimensional world. In 2001, mathematician and science fiction author Rudy Rucker published Spaceland, a modernized homage to Flatland that incorporates concepts from contemporary physics, including the fourth dimension. The enduring influence of Flatland illustrates a key point. Artistic explorations of dimensionality can make abstract mathematical concepts accessible to broader audiences, translating technical ideas into narratives and images that engage the imagination. This translational role of art and literature has become increasingly important as physical theories of dimensionality have grown more mathematically sophisticated and removed from everyday experience. In the early 20th century, the concept of a fourth dimension captured the imagination of avant-garde artists, particularly those associated with Cubism and Futurism. Pablo Picasso, Marcel Duchamp, and others experimented with representing four-dimensional perspectives in their paintings and sculptures. These artists were influenced not only by mathematical discussions of higher dimensions, but also by contemporaneous developments in physics, particularly Einstein's unification of space and time into four-dimensional space-time. Marcel Duchamp's 1912 painting Nude Descending a Staircase, number 2, represented the movement of a figure through time as a series of overlapping images, suggesting a four-dimensional perspective that encompasses both space and time. Similarly, Cubist paintings by Picasso and Georges Braque attempted to represent objects from multiple spatial perspectives simultaneously, hinting at perceptions beyond our usual three-dimensional view. These artistic experiments were not literal illustrations of scientific theories, but creative responses to the idea that reality might have dimensions beyond our direct perception. They challenged conventional modes of representation and invited viewers to consider how a four-dimensional reality might appear if we could somehow perceive it directly. As the 20th century progressed, science fiction emerged as a key venue for exploring the implications of extra dimensions. In 1941, Jorge Luis Borges published The Library of Babel, a short story describing an infinite library containing every possible 410-page book. While not explicitly about extra dimensions, the story's infinite library can be understood as a higher dimensional structure, with each book representing coordinates in a vast configuration space. Robert A. Heinlein's 1941 story, And He Built a Crooked House, describes a house built in the shape of an unfolded hypercube, a four-dimensional cube. When an earthquake causes the house to fold into a true hypercube, its residents find themselves navigating a structure with paradoxical spatial properties, where rooms connect in ways impossible in three dimensions. As scientific understanding of extra dimensions evolved, science fiction evolved with it. By the latter part of the 20th century, writers began incorporating more sophisticated concepts from theoretical physics. Greg Egan's novel Diaspora, published in 1997, describes civilizations existing in various dimensions, including purely digital realms. The novel explores how consciousness might experience and adapt to different dimensional environments, from three-dimensional space to abstract mathematical structures of much higher dimensionality. Film and television have provided some of the most vivid popular depictions of extra dimensions. The 1997 film Event Horizon suggests that a spacecraft equipped with an experimental gravity drive has traveled through a higher dimension, emerging transformed by contact with an apparently malevolent, higher dimensional reality. While scientifically inaccurate in many respects, the film captures the sense that extra dimensions might harbor phenomena entirely alien to our experience. The 1999 film The Matrix, while framed primarily in terms of virtual reality rather than extra dimensions per se, nonetheless explores how what we perceive as a three-dimensional reality might be a projection or subset of a more complex underlying structure. The film's famous red pill, blue pill scene dramatizes the philosophical question of whether we would choose to perceive a deeper reality if doing so disrupted our comfortable understanding of the world. More recently, the 2014 film Interstellar, directed by Christopher Nolan and developed in consultation with theoretical physicist Kip Thorne, features a climactic sequence in which the protagonist enters a higher dimensional space represented as a tesseract, a four-dimensional analog of a cube. Within this tesseract, time appears as a spatial dimension that the character can move through and interact with. While taking artistic liberties, the film attempts to ground its depiction of extra dimensions in contemporary physical theories, particularly concerning gravity and black holes. The 2016 film Doctor Strange draws on ideas from string theory and the multiverse to depict mystical practitioners who can manipulate reality by accessing higher dimensions. The film's kaleidoscopic visual effects, with cityscapes folding and replicating in impossible geometries, offer one of cinema's most elaborate attempts to visualize higher dimensional spaces in ways accessible to general audiences. Television shows like The Twilight Zone and The Outer Limits often explore dimensional anomalies, while more recent series like Stranger Things feature alternate dimensions adjacent to our own. The popular animated series Rick and Morty frequently depicts travel between dimensions, using the concept to explore philosophical questions about identity, possibility, and the nature of reality with a satirical edge. Video games have also embraced extra dimensions as both narrative and mechanical elements. Games like Portal and Antichamber challenge players to navigate non-Euclidean spaces that behave in ways impossible in ordinary three-dimensional geometry. Miegakure, a game still in development at the time of this writing, explicitly aims to give players the experience of navigating a four-dimensional world, allowing them to make moves through the fourth dimension to solve puzzles that would be impossible in three dimensions. Music, too, has drawn inspiration from the concept of extra dimensions. From the psychedelic explorations of 1960s rock, which often use spatial and dimensional metaphors to describe altered states of consciousness, to electronic compositions that attempt to create soundscapes evoking higher dimensional geometries, musicians have found rich creative potential in these scientific concepts. The band Boards of Canada's album, Tomorrow's Harvest, includes tracks with titles like Reach for the Dead and New Seed that evoke the mystery and otherworldliness associated with hidden dimensions and parallel realities. The electronic composer Autekri creates densely layered, algorithmically generated compositions that some listeners interpret as sonic representations of higher dimensional mathematical structures. Even humor has embraced extra dimensions as subject matter. The popular webcomic XKCD has featured multiple strips dealing with dimensionality, dimensional travel, and the mathematical properties of higher dimensional objects. Similarly, the animated series Futurama, created by mathematician turned cartoonist Matt Groening, frequently includes jokes and plot points involving higher dimensions, non-Euclidean geometry, and other abstract mathematical concepts. What accounts for the enduring appeal of extra dimensions in popular culture? Several factors seem relevant. First, the concept provides a scientifically grounded version of the ancient human intuition that there might be more to reality than what we directly perceive. From Plato's allegory of the cave to religious notions of heavenly realms, humans have long entertained the possibility that our immediate experience represents only a portion of what exists. Modern physical theories of extra dimensions give this intuition concrete mathematical form and potential experimental relevance. Second, extra dimensions offer rich narrative possibilities. They provide a scientifically plausible framework for imagining alternate realities, parallel universes, and modes of existence radically different from our familiar experience. For storytellers, they open doors to exploring philosophical questions about perception, reality, and the limits of human understanding in concrete, dramatic forms. Third, the visual and conceptual challenges of representing higher dimensions push artists to develop new techniques and approaches. How does one depict a four-dimensional object on a two-dimensional canvas or screen? How does one describe in linear language experiences that transcend our spatial categories? These challenges have stimulated artistic innovation across multiple media. Fourth, popular depictions of extra dimensions serve an important educational function, making abstract scientific and mathematical concepts accessible to broader audiences. While inevitably simplifying and sometimes distorting the underlying science, these creative works can nonetheless spark interest in the actual theories and stimulate public engagement with complex scientific ideas. The relationship between scientific theories of extra dimensions and their popular representations is not one way. While scientists obviously influence popular culture, popular depictions also shape how scientists themselves think about and communicate their ideas. Many physicists acknowledge the influence of science fiction on their early interest in theoretical physics. And when explaining their complex mathematical models to non-specialists, scientists often draw on metaphors and visualizations developed in popular contexts. This reciprocal relationship exemplifies what science studies scholars call the co-production of scientific and cultural knowledge. Scientific understanding is never developed in isolation from broader cultural currents, and cultural representations are increasingly informed by scientific concepts. The result is a complex ecosystem of ideas in which technical theories and popular imaginations mutually influence each other. Of course, popular representations of extra dimensions often diverge significantly from the scientific theories that inspire them. In fiction, extra dimensions frequently serve as plot devices enabling faster-than-light travel, contact with alien beings, or access to parallel worlds with different physical laws or historical trajectories. By contrast, the extra dimensions proposed in string theory and related frameworks are typically compactified at scales far too small to directly access and do not necessarily connect to alternate realities in the sense depicted in fiction. Similarly, while fictional portrayals often suggest that we might someday develop technologies to directly access or manipulate extra dimensions, most scientific theories propose that these dimensions are so tightly curled and their effects so subtle that they might only be detectable through highly specialized experiments involving enormous energies or extremely precise measurements. These discrepancies between scientific theories and their popular representations are not simply errors or misunderstandings. Rather, they reflect the different purposes and constraints of scientific and artistic endeavors. Science aims for precise, testable descriptions of physical reality, while art and fiction aim to explore human meanings and experiences through narrative, metaphor, and sensory engagement. Each approach has its own validity and value. Moreover, the speculative nature of scientific theories about extra dimensions creates a space where science and fiction can productively overlap. When scientific theories propose entities or phenomena far removed from direct observation, the line between scientific speculation and science-fictional imagination becomes less distinct. Both scientists and science fiction writers engage in disciplined, rigorous forms of speculation based on extending known principles into unknown domains. As we survey the representation of extra dimensions across popular culture, we find a rich tapestry of artistic responses to one of the most intriguing scientific possibilities of modern physics. From Abbott's Victorian allegory to contemporary virtual reality experiences, from avant-garde paintings to blockbuster films, creative minds have grappled with the implications of dimensions beyond our direct perception. These artistic explorations have not only entertained but also educated, making abstract concepts tangible and stimulating public engagement with fundamental questions about the nature of reality. In the next chapter, we will look to the future, exploring cutting-edge research and emerging approaches to understanding and potentially detecting hidden dimensions. As experimental physics pushes into new territory and theoretical frameworks continue to evolve, what might the coming decades reveal about the true dimensionality of our universe? As we look toward the horizon of scientific inquiry, the quest to understand higher dimensions stands at a fascinating crossroads. Theoretical frameworks have matured over decades, experimental approaches continue to evolve, and new technologies promise unprecedented insights into the fundamental nature of reality. In this final chapter, we explore the future of higher dimensional research and reflect on what this scientific journey reveals about our place in a potentially far more complex universe than our senses directly perceive. The immediate future of experimental searches for extra dimensions centers on several promising approaches. The Large Hadron Collider, after upgrades to increase its luminosity and energy, will continue its hunt for signatures of extra dimensions in high-energy particle collisions. While previous runs have not yielded definitive evidence, the increased collision rates and improved detectors of the upgraded facility might yet reveal subtle hints of dimensions beyond the familiar four. Looking further ahead, proposed next-generation colliders like the Future Circular Collider or the Compact Linear Collider could potentially reach energies several times higher than the LHC, expanding the parameter space in which extra dimensions might manifest. These facilities represent enormous investments of resources and international collaboration, reflecting the scientific community's commitment to pushing the boundaries of our understanding of fundamental physics. Beyond particle accelerators, precision measurements of gravity at small distances continue to improve in sensitivity. New experimental techniques using quantum optomechanics, where light is used to control and measure the motion of microscopic mechanical systems, may allow tests of gravitational forces at distances much smaller than currently possible. If large extra dimensions exist, deviations from Newton's inverse square law might be detected at these scales. Astrophysical observations offer another window into potential higher dimensional effects. Advanced gravitational wave observatories, successors to facilities like LIGO and Virgo, will achieve greater sensitivity and broader frequency coverage, potentially detecting subtler gravitational wave signals that might reveal the influence of extra dimensions on the propagation of gravitational radiation. Space-based observatories like the James Webb Space Telescope and its successors will provide unprecedented views of the early universe, constraining cosmological models with extraordinary precision. The detailed patterns in the cosmic microwave background radiation and the large-scale structure of galaxy distribution might contain hidden clues about the geometry of the universe, including its possible higher dimensional structure. Quantum information science represents a particularly intriguing new direction. As researchers develop increasingly sophisticated quantum computers and quantum simulators, new opportunities arise to explore the connections between quantum entanglement, information, and space-time geometry. The holographic principle, which suggests a profound relationship between gravitational theories in higher dimensions and quantum theories in lower dimensions, might be probed through novel quantum experiments that test the limits of entanglement and information processing. On the theoretical front, several developments promise to reshape our understanding of dimensionality and its role in fundamental physics. The concept of emergent dimensions, where what we perceive as spatial or temporal dimensions arise from more fundamental underlying structures, has gained traction in various approaches to quantum gravity. In these frameworks, dimensions themselves are not fundamental, but emerge as collective properties of more primitive quantum entities. Loop quantum gravity a leading competitor to string theory in the quest for quantum gravity, suggests that space itself is quantized at the Planck scale, composed of discrete units rather than being infinitely divisible. In some versions of this theory, the effective dimensionality of spacetime might vary with the energy scale at which it is probed, a phenomenon known as dimensional reduction. At very high energies, near the Planck scale, the dimensionality might effectively reduce from 4 to 2, with profound implications for the very concept of dimensionality in fundamental physics. Causal set theory, another approach to quantum gravity, models spacetime as a discrete set of events connected by causal relationships. In this framework, the continuous dimensions we experience emerge from the statistical properties of these more fundamental causal connections. Similar ideas appear in other discrete approaches to quantum gravity, including spin networks and causal dynamical triangulations. These theoretical developments suggest that our current understanding of dimensions as continuous, independent aspects of a spacetime manifold might be an approximation valid only at the relatively low energies and large scales of our everyday experience. At the most fundamental level, spacetime itself, including its dimensionality, might emerge from deeper quantum processes that defy our classical intuitions. The role of information in physics represents another frontier with implications for our understanding of dimensions. The increasing recognition that information is physical, not merely an abstract concept, has led to frameworks in which information processing plays a fundamental role in the structure of reality. Quantum information theory, with its concepts of qubits and quantum computation, provides new tools for thinking about how space, time, and dimension might emerge from more primitive informational or computational processes. These developments align with broader shifts in how physicists think about the relationship between mathematics, information, and physical reality. Rather than viewing mathematical structures as descriptions we impose on a pre-existing physical world, some theorists propose that mathematical structures themselves constitute reality, with the physical world we experience representing one manifestation of these deeper, abstract structures. In such a mathematical universe, as proposed by cosmologist Max Tegmark, dimensions would be aspects of the mathematical structures that define reality rather than independent physical entities. Another significant trend is the increasing dialogue between theoretical physics and other fields, from condensed matter physics to quantum information science to pure mathematics. Cross-fertilization between these disciplines has led to unexpected insights. Concepts from condensed matter physics, such as topological phases of matter, have found applications in understanding the possible configurations of extra dimensions in string theory. Similarly, advances in pure mathematics, particularly in fields like algebraic geometry and topology, have provided new tools for exploring the properties of higher dimensional spaces. This interdisciplinary approach extends to the relationship between theory and experiment. Rather than proceeding on entirely separate tracks, theorists and experimentalists increasingly collaborate to identify the most promising avenues for detecting signatures of new physics, including extra dimensions. This more integrated approach improves the odds of making meaningful discoveries, even in domains where the relevant phenomena might be extremely subtle or difficult to detect. As research on higher dimensions advances, it encounters both opportunities and challenges in the broader scientific and cultural landscape. On one hand, the exploration of fundamental physics, including extra dimensions, has been supported by substantial public and private investment. The construction of facilities like the Large Hadron Collider and the development of space-based observatories demonstrate societal commitment to pursuing knowledge even when its practical applications might not be immediately apparent. On the other hand, the increasingly abstract and mathematically sophisticated nature of theoretical physics presents challenges for public understanding and engagement. When theories involve 10 or 11-dimensional spaces and mathematical structures far removed from everyday experience, communicating their significance to non-specialists becomes difficult. This challenge underscores the importance of science communication and the creative arts in making these concepts accessible to broader audiences. Moreover, as the energy scales needed to directly test some aspects of higher dimensional theories push beyond what can be achieved with foreseeable technology, questions arise about the scientific status of these theories. If aspects of string theory or other frameworks incorporating extra dimensions cannot be directly tested, do they remain within the realm of science? Or do they become mathematical explorations that, while potentially valuable, lack the empirical grounding traditionally associated with scientific theories? These questions reflect broader debates about the philosophy of science and the criteria for evaluating scientific theories. Some philosophers and scientists argue for a strict adherence to falsifiability, the principle that scientific theories must make predictions that could potentially be shown to be false through observation or experiment. Others advocate more nuanced approaches, recognizing that in fundamental physics, the path from theoretical insight to experimental verification can be long and indirect. The history of science suggests that seemingly untestable theories have sometimes led to unexpected empirical consequences. When Einstein developed general relativity, the technology to test some of its more subtle predictions did not exist. Yet over time, as experimental techniques advanced, these predictions were confirmed with exquisite precision. Similarly, aspects of higher dimensional theories that seem beyond experimental reach today might become testable as technology and observational techniques evolve. Perhaps most importantly, the exploration of higher dimensions exemplifies the capacity of the human mind to transcend the limitations of direct sensory experience. That we can conceive of dimensions beyond those we perceive, develop mathematical frameworks to describe them, and devise experiments to indirectly probe their existence speaks to the remarkable power of human reason and imagination. As we conclude our exploration of hidden dimensions, let us return to the fundamental questions that have guided our journey. Are there dimensions beyond the familiar three of space and one of time? The honest answer is that we do not yet know with certainty. The theoretical case for their existence is compelling, particularly in frameworks like string theory that aim to unify our understanding of fundamental forces. But definitive experimental evidence remains elusive. What we can say with confidence is that the pursuit of this question has already enriched our understanding of physics, mathematics, and the nature of reality. It has led to profound theoretical insights, from the Kaluza-Klein unification of gravity and electromagnetism to the ADS-CFT correspondence connecting gravitational and quantum theories. It has stimulated the development of sophisticated mathematical frameworks for describing higher dimensional spaces and their properties. And it has inspired experimental approaches of extraordinary ingenuity and precision. Moreover, the concept of hidden dimensions reminds us of a profound truth about science. Our theories are not merely descriptions of what we can directly observe, but attempts to construct coherent mathematical models that explain the patterns in our observations and predict new phenomena. Sometimes these models lead us to postulate entities or structures, like extra dimensions, that lie beyond our immediate perception, but might nevertheless be essential components of physical reality. Looking to the future, the exploration of hidden dimensions will likely continue along multiple paths. Experimental physicists will develop increasingly sensitive instruments and techniques to search for indirect evidence of extra dimensions. Theoretical physicists will refine existing frameworks and perhaps develop entirely new approaches to understanding the dimensionality of reality. And these scientific endeavors will continue to inspire artistic, philosophical, and cultural responses that make these abstract concepts accessible to broader audiences. The universe, it seems, may be more vast, more intricate, more mathematically elegant than our unaided senses reveal. The three dimensions of space that form the arena of our everyday experience may be just the visible surface of a deeper, higher dimensional reality. And the key to understanding this reality may lie in the mathematics of tiny vibrating strings, the geometry of compactified dimensions, or perhaps in theoretical frameworks not yet conceived. As we stand at this frontier of human knowledge, we are reminded of both the remarkable progress we have made in understanding the fundamental nature of reality and the vast territories that remain unexplored. The quest to comprehend the true dimensionality of the universe embodies the essence of the scientific enterprise, the never-ending effort to push beyond the boundaries of current understanding, to discover deeper patterns and principles in the physical world, and to satisfy the uniquely human curiosity about our place in the cosmos. Perhaps most significantly, the study of higher dimensions helps us appreciate that reality might be far stranger and more wonderful than our limited perception suggests. The universe does not conform to our intuitions or preferences. It reveals itself through careful observation, mathematical analysis, and experimental ingenuity, often challenging our preconceptions and expanding our conception of what is possible. Whether or not extra dimensions ultimately prove to exist in precisely the forms currently theorized, the journey of exploring their possibility has already transformed our understanding of fundamental physics and enriched our appreciation of the complexity and beauty of the cosmos. It has reminded us that, in the words attributed to the biologist J.B.S. Haldane, the universe is not only stranger than we imagine, it is stranger than we can imagine. And yet, despite this strangeness, despite the mathematical abstraction and conceptual challenges involved in thinking about higher dimensions, human reason has proven remarkably capable of grasping at least aspects of this reality that extends beyond our direct sensory experience. This capacity for abstract reasoning, for constructing and comprehending mathematical models of realms we cannot directly perceive, represents one of the most remarkable features of human consciousness. As we conclude our journey, we might reflect on a passage from the physicist Richard Feynman. "The imagination of nature," he wrote, "is far, far greater than the imagination of man. Yet it is precisely through the exercise of human imagination, guided by mathematical reasoning and empirical observation, that we have been able to glimpse aspects of nature's imagination that extend beyond our immediate perception. The universe may be more vast, more intricate than our senses reveal. Hidden dimensions whisper the secrets of existence, waiting patiently for us to listen. Our journey to understand them continues, driven by the distinctly human desire to comprehend the universe in which we find ourselves and our place within it. Whether the ultimate nature of reality includes 10, 11, or more dimensions, or whether dimensions themselves emerge from more fundamental principles yet to be discovered, the quest to understand the true structure of the cosmos exemplifies science at its most ambitious and profound. It is a quest that connects the abstract mathematics of theoretical physics to the concrete technologies of experimental science, all in service of answering one of the most basic questions we can ask about the nature of the world. How many dimensions does reality have? As we gaze up at the night sky, contemplating the billions of galaxies revealed by our telescopes, we might reflect that even this vast cosmos might be just one manifestation of a deeper, higher dimensional reality. The visible universe, with all its stars and galaxies stretching across billions of light years, might be comparable to the shadow cast by a higher dimensional object, a projection onto the screen of our limited perception. This perspective invites both humility and wonder. Humility in recognizing the limitations of our perception and understanding. Wonder in contemplating the extraordinary richness and complexity of a reality that continues to reveal new depths as our scientific understanding advances. And so, our exploration of hidden dimensions concludes not with definitive answers, but with an invitation to continued inquiry, reflection, and imagination. The universe may indeed have hidden dimensions beyond what we see. Dimensions that shape the behavior of fundamental particles, the properties of forces, and perhaps even the origin and fate of the cosmos itself. The mathematics suggests it, theoretical physics requires it, and experiments continue to search for evidence of it. The final answer may emerge from the next generation of particle accelerators, from more sensitive gravitational wave detectors, from precision cosmological observations, or from theoretical breakthroughs not yet conceived. Or perhaps the question will evolve as our understanding deepens, with the very concept of dimensionality transformed by new insights into the nature of space, time, and physical reality. Whatever the outcome, the journey itself exemplifies the power of human curiosity and the capacity of the scientific method to probe realities far removed from our direct experience. From the initial insight of Kaluza that a fifth dimension might unify gravity and electromagnetism to the sophisticated framework of M-theory with its 11 dimensions, from early thought experiments about how four-dimensional objects would appear to three-dimensional beings to the cutting-edge simulations of higher dimensional phenomena. This exploration represents one of the most ambitious and profound endeavors in the history of science. As we end our journey through the hidden dimensions of reality, we carry with us the awareness that the universe may be stranger, more complex, and more mathematically elegant than our everyday experience suggests. And in that awareness lies an invitation to continued wonder, exploration, and discovery as we seek to understand our place in a cosmos that might extend far beyond the dimensions of our immediate perception. The universe may be more vast, more intricate than our senses reveal. Hidden dimensions whisper the secrets of existence, waiting patiently for us to listen.